How's that? Is that pretty good? I think so. All right, let's do 4 hours of we'll do 4 hours of physics today and then 4 hours of Anki. I think that's what it's gonna be. I need to throw out the trash in the bathroom. So let me do that real quick and then come back and we can get started. Oh, I might need some eye drops. We'll see. Yeah.
Everything we've done so far has been stationary fluids or static fluids, and we've been dealing with static pressure because all of the, we were trying to figure out what happens when everything's in a steady state. So now let's work on what happens when the fluid is actually moving. So let's imagine a pipe. Draw a pipe. Let's say one end of the pipe has a larger area than the other end, or at least a different area. Draw. So this is one end of the pipe. That's the other end of a pipe. I didn't draw it that well. And let's say it's filled with some fluid, some liquid actually, in our example. So there's just a bunch of liquid in this fluid, right? And let's say this area at the entrance is the area. Let's call that the area in. Area in. That's the area, the area of the opening into the pipe. And let's call this area out. The area of the opening coming out of the pipe. So let's think about what happens if this liquid is actually moving. And let's say it's moving into the pipe with the velocity v in, right? Let's think about how much volume moves into the pipe after t seconds. So after t seconds, if you think about it, you'd have this much area, and then if you think about what was right here, it will then be moved to the right by how much? Well, you could just go back to our basic kinematic formula. Distance is equal to rate times time. So the distance something travels is equals velocity times time. So after t seconds, after t seconds, whatever fluid was here, and it would have an area of about that much, whatever fluid was there would have traveled how much to the right? It would have traveled, let's assume that the pipe doesn't change too much in diameter or in radius from here to here. It would have traveled velocity times time. So v in times time. It could be meters or whatever our length units are. So after t seconds, essentially this much water has traveled into the pipe, right? you could kind of imagine a cylinder of water here. And once again, I know I made it look like it's getting wider the whole time, but let's assume that its width doesn't change that much over the t seconds or whatever units of time we're working at, right? So what is the volume of this cylinder of water? So the volume in over those seconds, right, over the t seconds is equal to the area, or kind of the top or the left-hand side of the cylinder. Let me draw the cylinder in a more vibrant color so you can figure out what we're trying to figure out the volume of. So it equals this side, the left side of the cylinder, the input area, times the length of the cylinder, and that's the velocity of the fluid times the time that we're measuring, times the input velocity times time, right? That's the amount of volume that came in. And now if that volume came into the pipe, and once again, we learned several videos ago that the definition of a liquid is a fluid that's incompressible, right? So it's not like, no fluid could come out of the pipe and all of the fluid just gets squeezed. The same volume of fluid would have to come out of the pipe, right? So that must equal the volume out, right? So whatever comes into the pipe has to equal the volume coming out of the pipe. And one assumption we're assuming is in this fraction of time that we're dealing with is also that there's no friction in this liquid or in this fluid, that it actually, it's not turbulent and it's not viscous. A viscous fluid is really just something that has a lot of friction with itself, and that it won't just naturally move without any resistance. And so when something is not viscous and has no resistance with itself and just moves freely without any turbulence, that's called laminar flow. And that's just a good word to know about. And that's the opposite of viscous flow. And different things have different viscosities. We'll probably do more on that. Like syrup or peanut butter has a very, very high viscosity. Even glass actually is a fluid with very, very high viscosity. While I don't know, I think there's some kinds of compounds and magnetic fields that you could create that are perfect laminar flow. But this is kind of a perfect situation. But anyway, in these circumstances, the volume in, because the fluid can't be compressed, it's incompressible, has to equal the volume out, right? Right? Well, what's the volume out over that period of time? Well, similarly, we could draw this bigger cylinder, right? That's the area out. And after t seconds, how much water has come out? Well, whatever water was here at the beginning of our time period will now be some distance will have come out, right? And we can kind of imagine a cylinder here. And what is well, I guess in this case, the width of the cylinder? Well, it's going to be the velocity that the liquid is coming out on the right-hand side. Or this is a capital V, right? Capital V is for volume, lowercase v is for velocity. So it's going to be the output velocity, that's a lowercase v, times the same time, right? So what is the volume that has come out in our time t? Well, it's just going to be this area times this width. So the output volume over that same period of time is equal to the output area of this pipe times the output velocity times time. And once again, I know I keep saying this, but this is kind of the big aha moment, is that in that amount of time, this cylinder, the volume in this cylinder has to equal the volume in this cylinder. So maybe it's not as wide or something like that. But their volumes are the same. You can't get more or less water. You can't get more water here all of a sudden than what's going in. And likewise, you can't put more water into the left side than what's coming out of the right side because it's incompressible. So these two volumes equal each other. So we know that the input surface area of the area of the opening onto the left hand of the pipe times the input velocity times the duration of time we're talking about is equal to the output area times the output velocity times the duration of time we're talking about. And if we want, the time is it's the same time in both sides of this equation. So we could say that the input area times the input velocity is equal to the output area times the output velocity. And this is actually called in fluid motion, this is called the equation of continuity, and it leads to some interesting things. We'll do some problems with it in a second. But one thing I want to introduce at this point as well is, what is the volume per second? Because this is also something we're going to deal with in a second, in probably the next video, because I'm about to run out of time. So we said in t seconds, we have this amount of volume coming in, and it's the same as coming in as coming out. So what is the volume per second? Well, it's this big capital VI per amount of time. And we call that flux. And we'll learn a lot about flux, especially when we start doing vector calculus. But flux is just how much of something crosses a surface in amount of time. How much of volume crosses a surface in amount of time. So in this case, the surface is this, the top of this, the left-hand side of the cylinder. And we're saying how much crosses an amount of time. We figured out it's that input volume, which crosses in every t seconds. And this is called flux. Flux. You've probably heard the flux capacitor in Back to the Future, and maybe we can think about is the surface too when we start doing vector calculus. But flux is the surface is this every t seconds, and this is called flux. Flux. You've probably heard the flux capacitor in Back to the Future, and maybe we can think about what they were in amount of time. Flux. Back to the Future, and maybe we can think about what they were trying to hint at. But let's see if we can use flux and these ideas to come up with some other interesting equations. Let me see if I have enough time. So we know that the volume per time is equal to flux. This is a big V. V is equal to flux. And actually, the variable people generally use for flux is R, and of course it's in meters cubed per second is its unit. We also know that the input area input times the input velocity, that's a lowercase v, is equal to the output area times the output velocity. Output velocity. And this is called the equation of continuity, and it holds true whenever we have laminar flow. And now, I'm about to run out of time. So in the next video, I'm actually going to use some of this information to figure out how much power is there in a system where we have fluid going through a pipe. See you soon. So let's say we have a pipe again. This is the opening, and we have fluid going through it, and the fluid is going with a velocity of V1. The pressure entering the pipe is P1, and then the area of this opening of the pipe is A1. And then it's a pipe, and it could even go up. So it goes up, and the other end is actually even smaller. And let's say that the fluid, the liquid, is exiting the pipe with velocity V2. The pressure that it exerts as it goes out. Let's say if there was like a membrane on the outside, how much pressure would exert on it as it pushes it out or whatever, or on the adjacent water, is P2. And the area of the smaller opening, it doesn't have to be smaller, is A2. And let's say that this opening is at a height of, I don't know, let's say this opening is at a height on average of H1. And let's say that this opening, so the water exiting this opening, is on average at a height of H2. We won't worry too much about the differential between the top of the pipe and the bottom of the pipe. We'll assume that these H's are much bigger relative to the size of the pipe. Let's say that this is H2. So with that setup, and remember, there's fluid going through this thing. There's fluid going through this thing. So with that setup, let's go back to what keeps showing up, which is the law of conservation of energy, which is in any closed system, the amount of energy that you put into something is equal to the amount of energy that you get out. So energy in is equal to energy out. Well, what's the energy that you put into a system, or that the system starts off with at this end? Well, it's the work that you input plus the potential energy at that point of the system, plus the kinetic energy of that at that point of the system. And then we know from the conservation of energy that has to equal the output work plus the output potential energy plus the output kinetic energy. A lot of times in the past, we just said that the potential energy input plus the kinetic energy input is equal to the potential energy output plus the kinetic energy output. But we could also, so the initial energy in a system can also be done by work. So we just added work to this equation that says that the energy in is equal to the energy out. So with that information, let's see if we can do anything interesting with this pipe that I've drawn. So what's the work that's being put into this system? Well, work is force times distance. So let's just focus on this. It's the force in times the distance in. And let's say that, so over a period of time t, what has been done? So we learned in the last video that over a period of time t, the fluid here might have moved this far. And what is this distance? This distance is the input velocity times whatever amount of time we're dealing with, so t. So that's the distance. And then what's the force? Well, the force is just pressure times area, and we can figure that out by just dividing force. We could divide this F by area and then multiply by area, so we get input force divided by area input times area input, right? And just divided and multiplied by the same number. That's pressure, that's area, is equal to the input distance over that amount of time, and that's velocity times time, times velocity input times time. So the work input is equal to, so the work input is equal to pressure, the input pressure times the input area times the input velocity times time, right? And what is this area? This area times velocity times time times this distance. Well, that's the volume of fluid that flowed in at over that amount of time, right? So that equals the volume of fluid over that period of time. So we could call that volume in, or volume I. I keep switching between the one and the I. But that's the input volume, right? And we know what? We know that density is just mass per volume, or that volume times density is equal to mass, or we know that volume is equal to mass divided by density. So the work that I'm putting into the system, I know I'm doing a lot of crazy things, but it'll make sense so far. The work that I'm putting into the system is equal to the input pressure times the amount of volume of fluid that moved over that period of time. And that volume of fluid is equal to the mass of the fluid that went in at that period of time. So we could call that the input mass divided by the density, right? Hopefully that makes a little bit of sense. And as we know, the input volume is going to be equal to the output volume. So the input mass, because the density doesn't change, is equal to the output mass. So we don't have to write an input and output for the mass. The mass is going to be constant. In any given amount of time, the mass that enters the system will be equivalent to the mass that exits the system. So there we go. We have an expression, the input mass divided by the density, right? Hopefully that makes a little bit of sense. Is just mass per volume, or that volume times density is equal to mass, or we know that volume is equal to mass divided by density. So the work that I'm putting into the system, I know I'm doing a lot of crazy things, but it'll make sense so far. The work that I'm putting into the system is equal to the input pressure times the amount of volume of fluid that moved over that period of time. And that volume of fluid is equal to the mass of the fluid. So the work that I'm putting into the system, I know I'm doing a lot of crazy things, but it'll make sense so far. The work that I'm putting into the system is equal to the input pressure times the amount of volume of fluid that moved over that period of time. And that volume of fluid is equal to the mass of the fluid that went in at that period of time. So we could call that the input mass divided by the density, right? Hopefully that makes a little bit of sense. And as we know, the input volume is going to be equal to the output volume. So the input mass, because the density doesn't change, is equal to the output mass. So we don't have to write an input and output for the mass. The mass is going to be constant. In any given amount of time, the mass that enters the system will be equivalent to the mass that exits the system. So there we go. We have an expression, an interesting expression for the work being put into the system. What is the potential energy of the system on the left-hand side? Well, the potential energy of the system, potential energy input, is going to be equal to what? It's going to be equal to that same mass of fluid, right, that I talked about, same mass of fluid, times gravity, times this input height, the initial height, times h1. And what's the initial kinetic energy of the fluid? Well, that equals the mass of the fluid, this mass right here, of that same cylindrical volume that I keep pointing to, times the velocity of the fluid squared. This is just, we remember this from kinetic energy, divided by 2. So what's the total energy at this point in the system over this period of time? How much energy has gone into the system? Well, it's going to be the work done, which is the input pressure. I'm running out of space. Actually, let me erase all of this. I'll probably have to run out of time too. That's okay. Better than being confused. Let me erase all of this. I want to erase everything. Hope I'm not boring you. Okay, we're ready to go now. So back to what we were doing. So the total energy going into the system is the work being done into the system, and I rewrote it in this format, which is the input pressure, we'll call that P1, times the mass divided by the density of the liquid, whatever it is. So this is work in plus, and what's the potential energy? Well, I wrote it right here. That's just mgh, where m is the mass of this volume of fluid. H is its average height. You can almost think of the center of mass. How high is the center of mass above the surface of the planet? Since we have a G here, we assume we're on Earth. So this is H1 because the height actually changes. So this is potential energy input plus the kinetic energy, mv1 squared over 2. So that is the kinetic energy input, right? And we know that this has to equal the energy coming out of the system, right? So let me clear up some more space here. Now that we wrote all that down neatly, we can get rid of it on this side, and we'll have space for our equations. I didn't have to delete this. I probably won't use this space up here. So this is going to be equal to the same thing on the output side, right? So this is going to be equal to the work out. So that'll be the output pressure times the mass divided by the density, plus the output potential energy, which will just be mgh2, plus the outbound kinetic energy, which would be mv2 squared divided by 2. I just realized I'm out of time, so I will continue this in the next video. See you soon. So just a quick review of what we were doing in the last video. We had this oddly shaped pipe, and I had the fluid coming in had an input velocity v1. The pressure on the left-hand side pushing to the right is p1, and its velocity, I already said velocity, and the area of this hole is a1. And what we and of everything has the same variables with the 2 on it is coming out of the pipe. And what we just set up in that last video is we said, well, by the law of conservation of energy, essentially the joules, the energy at this point in the system, or that we're putting into the system, has to be equal to the energy coming out of the system. And so we use that information to set up this big equation, but it's not too complicated. We figured out that the work going into the system was the input pressure times the mass of volume over some period of time, divided by the density of whatever type of liquid we had. The potential energy, this is just typically mgh, where the mass is the mass of this column of fluid, right? We're kind of saying how much work was done over some period of time t, essentially. That's the way I would think about it. How much energy was there over some period of time t? And the kinetic energy over that period of time would have been the mass of this volume of fluid times its velocity squared divided by 2. That's typical kinetic energy, right? And of course, that has to be equal to essentially the output energy. And so this is the output work, or essentially how much work a column of water could do on the output side. So, and it's an equivalent volume of water, remember that. So in some period of time t, whatever volume of water this was, in some period of time t, an equivalent volume of water, maybe it'll be a longer cylinder now, because it's going to be going faster. So on the output side, it's this longer cylinder that we're talking about, but it's going to be the same volume and the same mass. So what we say is that the output, the work that this column can do in that same amount of time, would be the output pressure times the mass of this column divided by the density of the column, which is the same because it's the density of the liquid is the same throughout, times the mass of this column, which is the same as the mass of this column, because the volume hasn't changed, and the density hasn't changed, so they're the same mass. Although now this column has more potential energy, right? It's up at H2, which I'm assuming is higher than H1. And then its kinetic energy is just the mass of this cylinder of fluid times its velocity squared, which is the output velocity divided by 2. So this is potential energy out, and this is kinetic energy out, and these equal each other. So this setup, this is Bernoulli's equation, but let's see if we can clean it up so that we can get rid of variables that we don't have to know about. So one thing that we see, there's an m in every term, so let's get rid of them. Divide both sides of this equation by m. Dividing both sides of this equation by m, we get that. And let's, I don't know, I don't like this density in the denominator here, so let's multiply both sides of this equation by density. And what we're left with is, let me write this in a vibrant color, P, the input pressure, plus, we're multiplying everything by this rho, this density. So we have input pressure plus rho g h1, the input height, the initial height, plus rho v squared over 2. You're probably expecting me to say rho v Wade, but no, this is rho, bad joke. This is rho v squared over 2. And that equals, we multiply both sides by rho, so we get this is the input velocity. The rho, so that equals the pressure out plus the density times gravity times the output height. I don't know, let's make everything consistent. I wrote 2's here, so let me say this pressure 2, this is height 2, plus rho times the velocity squared, the output velocity squared. This is Bernoulli's equation, and it has all sorts of what I would say is fairly neat repercussions. For example, it tells us that, let's assume that the height stays constant, so we could ignore these middle terms. If the height is constant, if I have a higher velocity, and this whole term is constant, then my pressure is going to be lower, right? Think about it. If height is constant, this doesn't change. But if this increases, if velocity increases, but this whole thing is constant, pressure has to decrease. Similarly, if pressure increases, then velocity is going to decrease. That might be a little unintuitive, but the other way it makes a lot of sense. When velocity increases, this pressure is going to decrease. And that's actually what makes planes fly and all sorts of neat things happen. But we'll get more into that in a second. But let's see if we can use Bernoulli's equation to do something useful. And you should memorize this, and it shouldn't be too hard to memorize. It's pressure, and then you have this kind of potential energy term, but instead of mass, you have density, and you have this kind of kinetic energy term. It's not kinetic energy anymore because we manipulated it some, but instead of mass, you have density. So with that said, let's do a problem. I'll keep this down here since you probably haven't memorized it as yet. Let me erase everything else. That's not how I wanted to erase it. Let me see if I can. Oh, that's how I wanted to erase it. I wanted to erase it like that without getting rid of anything useful. Okay, that's good enough. Then let me clean up all this stuff. Clean up this stuff. So let's say that I have a cup. A cup. I'll just draw a cup. Easier to draw sometimes than draw straight lines. Oh, that's too dark. Too purple. I'm using the super wide tool. Switch the length. Okay, so that's my cup. It has some fluid. Actually, let's say it has a top to it. It has a top to it, and I have some fluid in it. Maybe it happens to be red. We haven't been dealing with the red fluids as yet. So let me. Oh, I didn't want to do that. So let's just, there's a fluid there. And let's say that there's no air here. So this is a vacuum. And let's say have a cup. A cup. I'll just draw a cup. Easier to draw sometimes than to draw straight lines and all that. Oh, that's too dark. Too purple.
Did I go back?
I'm using the super wide tool.
I must have gone back.
Switch the length. Okay, so that's my cup. It has some fluid. Actually, let's say it has a top to it. It has a top to it, and I have some fluid in it. Maybe it happens to be red. We haven't been dealing with the red fluids as yet. So oh, I didn't want to do that. So let's just, there's a fluid there. And let's say that there's no air here. So this is a vacuum. And let's say that H, we don't know what units are, but let's say H meters below the surface of the fluid. So this is all fluid here, right? I poke a hole right there, and fluid starts spurting out. And my question to you is, what is this output velocity of the fluid as a function of this height? And let me tell you something else. Let's say that this hole is so small. Let's call the area of that hole A2. And let's say that the surface area of the water is A1. And let's say that hole is so small that the surface area of the water, let's say that A2 is equal to 1/1000th of A1. So this is a small hole relative to the surface area of this cup, right? So with that said, let's see what we can do about figuring out the velocity coming out. Well, Bernoulli's equation tells us that the input pressure plus the input potential energy plus the input kinetic energy is equal to the output, et cetera, et cetera, et cetera. So what is the input pressure? Well, the input pressure, the pressure at this point, there's no air or no fluid above it, so the pressure at that point is zero. Input pressure is zero. What is the input height? Well, let's just assume that that the hole is done at height 0, h equals 0. So the input height, h1, is just h, right? If this is 0, then this height right here is h. And what is the input velocity? Well, we know from the continuity equation, or whatever that thing was called, we know that the input velocity times the input area is equal to the output velocity times the output area. And we also know that the output area is equal to 1/1000th of the input area, right? So this is area 2. So we know that the input velocity times area 1 is equal to the output velocity times 1/1000th of area 1. So we could say area 1 over 1,000. Divide both sides by area 1. So we know that the input velocity is equal to V2 over 1,000, right? So that's good to know. So these are the three inputs into the left-hand side of Bernoulli's equation. And what's on the right-hand side of Bernoulli's equation? Well, what's P2? What's P2? What's the pressure at this point? Well, I just ran out of time. I'll continue this into the next video. So where we left off, we had this canister, because it had a closed top and had a vacuum above the fluid, and the fluid on top had I'm using the big marker right now. The fluid on top had an area of A1, and I poked a little hole with a super small area A2, and I said that the area of A2 is so small it's 1/1000th of area 1. And then we used the continuity equation. We said, well, the velocity, the rate at which the surface is moving up here, so that's V1, times area 1, right, times the whole surface area of the liquid, has to be equal to the output velocity, which we're trying to figure out as a function of everything else, times this output area. And then we say, well, and I don't remember. Let's see, I made a mistake. So I don't know if I did this in the last video or I did this in my mistake video. But anyway, so we know that the initial, this top velocity times this top area is equal to the output velocity times, instead of writing area 2, we could write area 1 over 1,000, right? We could write area 1 over 1,000. We would still have the area 1 here. And then you can get rid of the area 1 on both sides. And then you're saying that the output velocity is equal to essentially, the velocity up here is equal to the rate at which the top of the surface moves down is equal to 1/1000th of the velocity of the liquid spurting out of this little hole. So now with that, we actually have the three variables for kind of the right-hand side, the left-hand side of Bernoulli's equation. And what are the variables on the left-hand side? Well, what is the pressure at this point where we have a hole? Well, and this is an important thing. When we talk about, Bernoulli's, let me rewrite Bernoulli's equation. It's P1 plus rho G H1 plus rho V1 squared over 2 is equal to pressure 2 plus rho G H2 plus rho V2 squared over 2. We figured out all of these terms. So now let's figure out the things that we have to input here. So what is the pressure at point 2? And this is the important thing. You might want to say, and this was my initial reaction too, and that's why I made a mistake, is that, oh, well, what's the pressure at this depth in the fluid? And that's not what Bernoulli's equation is telling us. The Bernoulli's equation is telling us actually what is the external pressure at that hole, right? How much, when we did the derivation, we were saying how much work. This was kind of the work term, although we played around with it a little bit, right? But if we look at the water that's spurting out of the hole, it's not doing any work because it's not actually exerting force against anything. So it's not actually doing work. So when we think about the pressure, the output pressure, it's not the pressure at that depth of the fluid. You should think of it as the pressure at the hole, the external pressure at the hole. And in this case, there is no external pressure at the hole. If there was, let's say that if we closed the hole, then at that point, sure, the pressure would be the pressure that's being exerted by the outside of the canister to contain the water, in which case we would end up with no velocity. The water wouldn't spurt anywhere. But now we're saying the external pressure is 0. That's what the hole essentially creates. So we're going to say that P2 is 0. So this is 0. So this pressure was 0 because we're in a vacuum, and then P2 is also 0. So both of these are 0. Remember, that's kind of the external pressure. It's the pressure. P1 is the pressure, external pressure to the input to the pipe, and you can kind of view this as a pipe, right? I could redraw that cup as kind of like this. Well, I could redraw it as a pipe, like it looks like. Well, actually, no. Undo that. It has a big hole on the top, and it goes down some level to a super small hole like that. And this would be a vacuum, and then the fluid is just going in and it's spurting out at this end, right? So anyway, the pressure going into the pipe is 0, and we said since we put a hole, the pressure coming out of the pipe is 0. So we're doing no work. And what is this term? Well, this was the potential energy term, and we said that H1 is equal to H is equal to, we're saying that this is 0 height. So now this simplifies to rho times gravity times H plus rho times V1 squared. Well, V1 we said is equal to this. So rho over 2 times V2 over 1,000 squared, right? I just substituted V2 over 1,000 for V1. That equals the pressure at the hole, the external pressure at the hole, which is 0, plus, what is H2? Well, this is H2 right here, which we said is 0. We determined that the hole was poked at height 0. So this is also 0. So that equals essentially this kinetic energy-like term. It's not exactly kinetic energy. It's rho times V squared 2. V squared divided by 2. Now, one thing that we can immediately see is that we have all these rhos on both sides of the equation, so we can divide both sides by rho. We get rid of all of those. And then we can multiply both sides of the equation by 2, and we get 2GH is equal to, plus this term, V squared, V2 squared, over, what's 1,000 squared? Over 1 million. Over 1 million. And that is equal to V2 squared. Now, we could do we could do the exact thing. We could subtract 1 over 1,000,000 V2 squared from both sides, and we would get, 0.9999999 V2 squared. But let's just say, for the sake of simplicity, or let's say if this wasn't 1,000, let's say this was 1,000,000. So this surface area was much bigger. We see that this term becomes very, very, very small. And if that hole is 1/1,000,000th of the surface area, then it becomes really insignificant. So we can ignore this term because it just makes things complicated. And we're assuming this is a really, really large number, that this hole is much smaller than that, than the surface area of the fluid. And we, this is like poking a hole in Hoover Dam, right? Hoover Dam is backing up this huge lake, and you poke a hole in it. So that hole is going to be this very small fraction of the surface area of the fluid. And you can only make this assumption when that output hole is much smaller than the input hole. But with that said, what is the output velocity? Well, the velocity is going to just take the square root of both sides. This is square root of, 2gh. So that is the output velocity. And what is the amount of liquid that flows out per second? Well, we figured that out already. It's kind of like a column of fluid that comes out. So per second, the length of the column of fluid will be the velocity times time. And then the cross section of that column is equal to the output area. So if I wanted to know the flow coming out, it would be the flow coming out, or the flux coming out, would be equal to the holes area times the output velocity, and that would equal the area times the square root of 2gh. And we could use that to actually solve problems in the future, if we had actual numbers. Anyway, I only have a minute and a half left, so I'll see you in the next video. Before we move on, I just wanted to make sure you understood that last point I made at the end of that last video. We said that the pressure kind of inputting into towards the heart.
I watched these.
1840s. Passed with over R over 2 to the.
I guess we did, huh? I don't remember when. Is it? No, we just did this one.
Inputting into this, before we move on, I just wanted to make sure you understood that last point I made at the end of that last video. We said that the pressure kind of inputting into this, we could view this cup with a hole in it as essentially a pipe, where the opening on the top of the cup is the input.
Hold on, I'll be right back.
pipe, and this little mini hole is the output to the pipe. And we say that this is a vacuum. Let's say this is a vacuum all around. I know when I drew it last time I closed it, but maybe above, we have a vacuum everywhere. Since there's a vacuum everywhere, the pressure at this point, P1, is equal to 0. And the point I wanted to make is because we have a hole here, the pressure at that point, at P2, is also equal to 0. You can almost view it as maybe the atmospheric pressure at that point, but since we're in a vacuum, that pressure is 0. And that might have been a little confusing to you because you said, well, wait, I thought at depth, if I had a point, let's say at that same height, that I would actually have a pressure at that point of rho GH. And that's true. That's completely true. You do have an innate pressure in the liquid at that point of rho GH. And actually, that's what's causing the liquid to come out. But that's actually taken care of in the potential potential energy part of the equation. So let me rewrite Bernoulli's equation. The input pressure plus rho GH1 plus rho V1 squared over 2 is equal to the output pressure plus rho GH2 plus PV2 squared over 2. And I think you understand this term is pretty close to 0 if the rate at which the surface moves is very slow if the surface area is much bigger than this hole. Just like if you poked a hole in Hoover Dam, that whole lake is going to move down very, very slow, like 1 trillion of the speed at which the water's coming out at the other end. So you could ignore this term. And then we also defined that the hole was at 0. So H2, the height of H2 is 0. And so it's simplified down to the input pressure, the pressure at the top of the pipe or at the left side of the pipe, plus rho GH1. And this was this isn't potential energy. This is, this was kind of the potential energy term when we derived Bernoulli's equation. And that equals the output pressure, or the pressure at the output of the hole, at the right side of the hole, plus the kinetic energy, PV2. The kinetic energy term, because this actually doesn't add up completely to kinetic energy because we manipulated it. And I just wanted to really make the point that this is definitely 0. I think that is clear to you because we have a vacuum up here. So the pressure at that point is 0, so we could ignore that. And so the question is, what is the pressure here? And I said, well, this pressure is 0 because we have a vacuum here. If I were to say that the pressure over here at this hole is equal to PGH, let's say that I said that the pressure at that hole is actually equal to PGH, so this is H, then I would have the situation where PGH is equal to PGH plus PV squared over 2. And what does that mean? That when I say that pressure at the output of the pipe is PGH, that means that I'm applying some pressure into that hole. And essentially that pressure I'm applying into the hole is exactly just enough offset to offset the pressure at this depth. And because of that, none of the water will move. You can imagine if this is the hole, let's say that's the opening of the hole, and I have some water particles or some fluid particles. Let's say that these are the atoms. These are the atoms. We're saying innately at any point, let's say at this, sure, there is a pressure at this point that's equal to rho GH. But this is P2, how much pressure I'm exerting on this end of the hole. This is P2. And if I exert rho GH at this end, if I exert rho GH at this end, then these molecules that are just about to exit the hole aren't going to exit because they're going to get the same pressure from every direction. So what we said in the last video, and I really want to, because this is a subtle point, is that the outside pressure being on the outside part of the hole is 0. And because of that, we end up, this term is 0, and we essentially end up with the change in the potential energy all becomes kinetic energy, which is something we're familiar with from just our kinematics and our energy equations. Well, anyway, with that out of the way, let me do another problem. And actually, I will do that next problem in the next video, just so we have a clean cut between videos. See you soon. Let's say I have a horizontal pipe that at the left end of the pipe, the area, cross-sectional area, so I'll call that area 1. Let's say that is, I don't know, equal to 2 meters. Yeah, let's use simple numbers. 2 meters squared. Let's say it tapers off. So that the area, the cross-sectional area at this end of the pipe, so area 2 is equal to, I don't know, half a meter, half a square meter. And let's say that, just the typical, we have some velocity at this point of the pipe, which is V1, and then the velocity exiting the pipe is V2. And let's say that the external pressure at this point, essentially being applied rightwards into the pipe, let's say that pressure 1 is, I don't know, let's say it's 10, let me write in a bold color. Let's say it's 10,000 pascals. And let's say that the pressure at this end, so the pressure 2, and so that's the external pressure at that point in the pipe. Let's say that that is equal to, I don't know, let's say it's equal to 6,000 pascals, right? And so given this information, let's say we have water in this pipe. There's just generally, so I could just throw water. And we're assuming it's laminar flow, so there's no a friction within the pipe and there's no turbulence and all of that. So using that, what I want to do is I want to figure out how much, what is the flow or the flux of the water in this pipe. So how much volume goes either into the pipe per second or out of the pipe per second. And we know that those are going to be the same numbers because of the equation of continuity. So we know that the flow, which is R, which is volume per amount of time, that is the same thing as the input velocity times the input area, right? So the input area is 2, so it's 2v1. And that also equals the output area times the output velocity, so it equals 1/2 v2. And then we could rewrite this that v1 is equal to 1/2 r, and that v2 is equal to 2r. So this immediately tells us that v2 is coming out at a faster rate, right? Just based on the size of the openings. And then we also know, because V2 is coming out at a faster rate, but we also know because we have much higher pressure at this end than at this end, that the water is flowing to the right. The pressure differential, the pressure gradient is going to the right. So the water is going to spread out at this end and it's coming in at this end. So let's use Bernoulli's equation to figure out what the flow through this pipe is. So Bernoulli's equation, let's just write it down. P1 plus rho G H1 plus 1/2 rho V1 squared is equal to P2 plus rho G H2 plus 1/2 rho V2 squared. Well, this pipe is level, right? The height at either end is the same. So these H1 is going to be equal to H2. So these two terms are going to be equal. So we can cross them out. We can subtract that value from both sides. And we're just left with P1. What's P1? P1 is 10,000 pascals. So start substituting numbers. 10,000 pascals plus 1/2 rho times V1 squared. Well, what's V1? Well, that's R over 2. We figured that out here. V times R over 2 squared is equal to P2. That's 6,000 pascals. Plus 1/2 rho times V2 squared. We figure out what V2 is. V2 is 2R. 2R squared. Let's just do some simplification. So let's subtract 6,000 from both sides. 4 thousand plus, let's see, we get r squared over 4 and then a 1/2. So we'd have rho r squared over, this is over 4 over 1/2, so it's over 8 is equal to, we already subtracted the 6,000 from both sides. So we'll have 1/2 times r squared times 4. So this is 2 rho r squared. See, we could multiply both sides of this equation by 8 just to get rid of this in the denominator. So we get 32,000 plus rho r squared is equal to 16 rho r squared. Subtract rho r squared from both sides of this equation, we get 32,000 is equal to, well, this is 1 rho r squared, this is 16 rho r squared, so this is 15 rho r squared. And then what's rho? What's the density of water? Well, the density of water is 1,000 kilograms per meter cubed, so this is 1,000. So let's divide both sides by 15 times rho. So let me switch colors. So we get r squared is equal to 32,000 divided by 15 rho. Rho is 1,000, so r squared is equal to 32,000 over 15,000, which is the same thing as 32 over 15. So r is equal to the square root of 32 over 15. That's going to be meters cubed per second. Let's see. Let's get my calculator. Handy calculator. Did I actually remove my calculator? I think I did. Let's get my calculator going. So I get 32 divided by 15 is equal to 2.1, and then I take the square root of that. 1.46. So the answer is r is equal to 1.46 meters cubed per second. So that is how much, that's the volume of water that is either entering the system in any given second or exiting the system in any given second. And we can figure out the velocities too, right? What's the velocity exiting the system? Well, it's 2 times that. So it's like 2.8 meters per second exiting the system. And going in, it is half that. So it's like 0.8 meters per second. But anyway, hopefully it is half that. So it's like 0.8 times that. So it's like 2.8 meters per second exiting the system. And going in, it is half that. So it's like 0.8 meters per second. But anyway, hopefully that gives you, actually 0.7 meters per second. That gives you a bit of an intuition, more intuition on fluids. And that's all I'm going to do for today. I'll see you in the next video, and we're going to do some stuff on thermodynamics.
Check out this
Oh. Okay.
Let's talk about the vent.
You're so loud, buddy.
Check out the.
Yeah, I'll be right back. I'll just clean up a little bit.
Now, check out this lid that I can put on the empty box. Let's say there is no, check out this empty box. Now, check out this lid that I can put on the empty box. Let's say there is no resistance, so that if I gave this lid a little nudge, it just keep moving with a constant speed. Let's say there's no air resistance, no resistive forces at all. Now, what I'm going to do, I'm going to stick a fluid, let's say water, and I'm going to fill it to the brim, all the way to the top. This thing was overflowing. This goes all the way to the top. Now what happens is you take this lid, you go to slide it across again, you give it a little nudge, it doesn't keep going, it slows down and stops. You give it another nudge, it slows down and stops. The fact that this fluid's in here now is resisting the motion, that's because it's viscous. What do I mean by that? I mean that when this lid was moving across the top, the fact that this fluid was in contact with the lid caused this topmost layer to start moving with the same speed as the lid. There's adhesive forces between this fluid and the lid on an atomic and molecular level. This fluid gets pulled with it.
Tomato right there.
And so it resists the motion, but it's worse than that, because if this topmost layer gets pulled this way, then the layer right below it gets pulled by the topmost layer, and this secondmost layer pulls this thirdmost layer, and this keeps going down the line, and what you get is a velocity gradient, is the fancy name for it, which just means that this velocity of this fluid gets smaller and smaller. Once you get down to the bottom, well, now the fluid is in contact with this surface at the bottom, and this surface at the bottom is not moving. This fluid that's at the lowest most point doesn't move at all. All right, so that's why this lid slowed down. When we gave it a nudge, it was dragging that fluid along with it. And if it exerts a force to the right on the fluid, then the fluid is going to exert a force, by Newton's third law, to the left on the lid, and I'm going to call this a viscous force. I'm going to call it FV. So what does this depend on? What does this viscous force depend on? One thing it depends on is the area, and not the whole area of the lid. It's just the area of the lid that's actually in contact with the fluid. So if you imagine the dimensions of this box would only expand here. So it's only that part of the lid that's actually in contact with the fluid. So that area, and it's proportional to that area. The bigger that area, the more fluid you're going to be dragging, the larger the viscous force. That makes sense. So it's this third law to the left on the lid, and I'm going to call this a viscous force. I'm going to call it FV. So what does this depend on? What does this viscous force depend on? One thing it depends on is the area, and not the whole area of the lid. It's just the area of the lid that's actually in contact with the fluid. So if you imagine the dimensions of this box would only expand here. So it's only that part of the lid that's actually in contact with the fluid. So that area, and it's proportional to that area. The bigger that area, the more fluid you're going to be dragging, the larger the viscous force. That makes sense. So it's this area here. And something else that it depends on is the speed with which you drag the lid. So the faster I pull the lid, well, it's actually in contact with the fluid. So if you imagine the dimensions of this box would only expand here. So it's only that part of the lid that's actually in contact with the fluid. So that area, and it's proportional to that area. The bigger that area, the more fluid you're going to be dragging, the larger the viscous force. That makes sense. So it's this impact with the fluid. So that area, and it's proportional to that area. The bigger that area, the more fluid you're going to be dragging, the larger the viscous force. That makes sense. So it's this area here. And something else that it depends on is the speed with which you drag the lid. So the faster I pull the lid, well, the faster I'm going to be pulling this water. The bigger that force, which means the bigger the viscous force, the more fluid you're going to be dragging, the larger the viscous force. That makes sense. So it's this area here. And something else that it depends on is the speed with which you drag the lid. So the faster I pull the lid, well, the faster I'm going to be pulling this water. The bigger that force, which means the bigger the viscous force, so it's proportional to the speed as well. It's inversely proportional to the depth of the fluid. I'll call that D. And then it depends on one more thing. It depends on the viscosity of the fluid, maybe the most important factor in this whole discussion. Eta is going to be called the viscosity of the fluid, or the coefficient of viscosity. And what this number tells you is how viscous, how thick, essentially, the fluid is, how much it resists flow. And so coefficient of viscosity, so to give you an idea, honey or corn syrup would have a large viscosity, water would have a smaller viscosity coefficient, and gases would have a coefficient of viscosity even less. So what are the units of this coefficient of viscosity? Well, if we were to solve for the eta, what would we get? We get force divided by area. So this would be force divided by area and multiplied by the distance divided by the speed. What units do these have? Force is in newtons, distance is in meters, area is in meters squared, speed is in meters per second. So bring that second up top because it was divided in the denominator. So it goes up top. And what am I left with? Meters cancels meters. And I'm left with the units of viscosity as being newtons per meter squared times a second. But a newton per meter squared is a Pascal. So this is Pascal seconds. So these units are a little strange, but the units of eta, the coefficient of viscosity, is a pressure times a time, Pascal seconds. But some people use the unit poise, and 1 poise is equal to 1/10 of a Pascal second. Or in other words, 10 poise, and it's abbreviated capital P, is 1 Pascal second. And so you'll often hear this unit poise as a measure of viscosity. So what are some real life values for the viscosity? Well, the viscosity of water at 0 degrees Celsius is, and I'm not talking about ice, but water that's actually at 0 degrees but not frozen yet, is about 1.8, but 1.8 millipascal seconds. And another way to say that, look at millipascal seconds, that would be a centipoise, CP. Because a poise is already 1/10 of a Pascal second. Remember, 1 poise is 1/10. And so a centipoise is really a millipascal second. Or water at 20 degrees Celsius is 1.0 millipascal seconds, or centipoise. And you can see there's a huge dependency on temperature. The viscosity is highly dependent on temperature. The colder it gets, the more viscous a fluid typically gets, which you know, because if you start your car and it's too cold outside, that car's not going to want to start. That oil inside is going to be more viscous than it's prepared for, and that engine might not start very easily. Blood typically has a viscosity between 3 to the viscosity is highly dependent on temperature. The colder it gets, the more viscous a fluid typically gets, which you know, because if you start your car and it's too cold outside, that car is not going to want to start. That oil inside is going to be more viscous than it's prepared for, and that engine might not start very easily. Blood typically has a viscosity between 3 to 4 millipascal seconds, or centipoise. And then engine oil can have viscosities in the hundreds, around 200 centipoise. And then gases would have viscosities that are even less. Air has a viscosity of around 0.018 centipoise. Now, it's important to note, if a fluid follows this rule for the viscous force and the coefficient of viscosity does not depend on the speed with which this fluid is flowing or with which you pull this lid over the top, does not depend on that, then we call this a Newtonian fluid. Then it's a Newtonian fluid. But if the coefficient of viscosity does depend on the speed with which the fluid is flowing or the speed with which you pull this lid, then it would be a non-Newtonian fluid. So if this coefficient of viscosity stays the same regardless of what the speed is, it's a Newtonian fluid. If that's not the case, it'd be a non-Newtonian fluid. Now, you might be thinking, well, this is kind of stupid. I mean, how many cases are we going to have where you're trying to pull a lid over a box? You've probably never tried to do that in real life, but this is just a handy way to determine the viscosity. Once you know the viscosity, you can apply this number. This is a constant of the fluid. Now, anywhere that this fluid is flowing, now that you've measured it carefully, you could determine what kind of flow rate you would get. So imagine, let's get rid of all this stuff here. Say you had a stationary tube or a pipe and there was a fluid flowing through it. Maybe it's a vein or a vessel and it's blood flowing through it. Anyways, now it's stationary though. Both the top and the bottom are stationary. So that means the fluid near the top and the fluid near the bottom aren't really moving, but it's the fluid in the middle that's moving fastest and then slightly less fast. And you get this somewhat parabolic type velocity gradient where it gets bigger and bigger and then it gets smaller and smaller. And so the velocity profile might look something like this. And if we wanted to know how much volume of fluid, how many meters cubed of fluid pass by a certain point per time, we can figure that out. There's a formula for this. The volume per time, the meters cubed per time. The formula is called Poiseuille's law. And it says this, it says the volume that will flow per time is dependent on delta P times pi times r to the fourth divided by 8 eta times L. Now this is a crazy equation. Let's break this thing down and see what it's really talking about. So here's Poiseuille's law. So this delta P is referring to the pressure differential. So there'll be pressure on this side. We'll call it P1. There'll be pressure on this side, P2. If those are the same, this fluid is not going to be flowing very long. There has to be a difference. If we want the fluid to flow to the right, P1 has to be bigger than P2, and the greater the difference, the greater this difference, P1 minus P2, the more volume that's going to flow per time, and that makes sense. And then pi is a geometric factor, r to the fourth. This r is referring to the radius of the tube, so that's r. And then 8, and eta we know. Eta is the viscosity. So this is the viscosity of the fluid, and the volume flow rate's inversely proportional to the viscosity, because the more viscous the fluid, the more it resists flowing and the less meters cubed you'll get per second. And it's inversely proportional also to the length of the tube. The more tube this fluid's got to flow through, the smaller the volume flow rate. So this is called Poiseuille's law. It's useful in a lot of medical and engineering applications for whenever you want to determine the volume flow rate. Now, you've got to be careful. We're assuming this is a Newtonian fluid. That means eta is not a function of the speed of the fluid. We're also assuming you have nice streamlined laminar flow. So laminar flow means these layers of fluid stay in their lane. Basically, they do not cross over. Once you start getting this, you'll start getting turbulence. And once you get turbulence, you'll need a much more complicated equation to describe the dynamics of this. So we're assuming no turbulence and a nice Newtonian fluid. And if that's the case, Poiseuille's law gives you the volume that flows through a pipe per time.
That's pretty neat. Wow. Turbulence.
Okay, so we saw that if you had nice laminar streamlined flow, Poiseuille's law told you how much volume per time would flow through a pipe. But how do you know when you're going to have a nice laminar flow? What determines when this thing becomes chaotic? What determines when these start to cross, these layers of flowing water or fluid? How do you know when they're going to start to cross, which is going to cause these vortices and eddy currents? When will this happen? Turns out there's a way to predict it. It's hard. This is very hard, in fact. Not only is it hard to predict it, once you know that it's going to happen, once you know things are going to become turbulent, it's even harder to try to describe the behavior. Typically, you have to resort to a computer simulation rather than an analytical calculation. But there is a number. It's called the Reynolds number. And what this number does is it gives you a way to predict what's the first speed, what's the critical speed, where if you went over this speed, if the fluid were to flow faster than this speed, it would become turbulent. The flow would become chaotic. The way you find it is you take this Reynolds number, I'm going to call that R, you multiply that by the viscosity. And remember, eta, this Greek letter we were using for the viscosity. You divide by 2 times the density of the fluid multiplied by the radius of the tube. And this gives you the first speed where you would expect turbulence. Now, if you measure the Reynolds number, to give you an idea, for blood, because this comes up a lot when you're talking about blood flow in the aorta, you might worry that there might be turbulence. For blood, the Reynolds number is around 2,000, and it's unitless. It has no dimensions. There's no units here. All the units cancel out. And the Reynolds number is a unitless, dimensionless quantity. So knowing the Reynolds number gives you a way to predict what's the first speed where you might expect turbulence, and therefore the first speed where you might expect Poiseuille's law to not give you an accurate description of the flow of the fluid. The first speed where you might expect turbulence, and therefore the first speed where no units, the Reynolds number. If you measure the Reynolds number, to give you an idea, for blood, because this comes up a lot when you're talking about blood flow in the aorta, you might worry that there might be turbulence. For blood, the Reynolds number is around 2,000, and it's unitless. It has no dimensions. There's no units here. All the units cancel out. And the Reynolds number is a unitless, dimensionless quantity. So knowing the Reynolds number gives you a way to predict what's the first speed where you might expect turbulence, and therefore the first speed where you might expect Poiseuille's law to not give you an accurate description of the flow of the fluid. If you took a glass of water and a needle, and you took that needle and you very carefully, if you took a glass of water and a needle, and you took that needle and you very carefully dropped it on the water, it would stay there. And it's not because it's floating. This needle would not be floating on the water. This needle is more dense than water. And we know that if it's more dense, then it should sink. So it's not floating. It's actually just sitting on the surface because there's surface tension. Water is a liquid that's capable of having a significant amount of surface tension. And you know it's surface tension because if you were to come in here and exert a little force down, breaking the surface tension or pushing this needle just below the surface, then it would sink. It would sink like a stone and just drop immediately to the bottom of the cup. So why does water have this property of surface tension? It has to do with the fact that the water molecules within this liquid are attracted to each other. This water molecule can form hydrogen bonds with the other water molecules around it, and it gets pulled toward them. And there's a term for this. We call this cohesion. So the fact that water molecules and other liquid molecules are attracted to each other is called cohesion. But what does this have to do with surface tension? Well, the key is these water molecules would like to bunch together. They want to group together if they can. So what would this water molecule do? I mean, which way is he going to go? How does he pick which one to group with? There's a problem. Here in the bulk of the liquid, he can't decide, or in other words, let's just say got pulled toward this molecule. Well, it's also getting pulled to the left by all of this. By this one's pulling it back to its original position. This one's pulling it back to its original position because there will be a component of that force that'll point in the direction of its original position, as well as this one to the left. So these are restricted. These molecules here in the bulk of the liquid have too many other water molecules around them dictating where they need to be, because if they tried to get displaced, it'd pull them back to that position. However, at the surface, there's no water molecules above them. These are freer, they're less restricted. So that allows these water molecules on the surface to group together a little better, form stronger, tighter bonds, closer spacing at the surface in such a way that they form a tension that's not present in the bulk of the liquid. Yes, these water molecules down below will prevent them from just grouping into one big clump in the center, but since they're less restricted, they can form these tighter bonds here at the surface, and this allows it to support a pressure from above. So this allows it to support a certain amount of weight, which allows the needle to rest on the surface. A few practical applications of this, one clinical: if there's bile present in urine, you can detect its presence because it lowers the surface tension of urine. So it gives you a test of whether the liver is metabolizing things the way it should. Another application is if you go camping and you're in the tent, it's raining, and the tent gets raindrops on it. Most tents will keep the water from seeping through, but you're going to be tempted. You're going to be sitting in here, you're going to be like, that looks cool, and you're going to touch it, but you're not supposed to touch it, because as soon as you touch it, you may break the surface tension. And once you break the surface, it lowers the surface tension of urine. So it gives you a test of whether the liver is metabolizing things the way it should. Another application is if you go camping and you're in the tent, it's raining, and the tent gets raindrops on it. Most tents will keep the water from seeping through, but you're going to be tempted. You're going to be sitting in here, you're going to be like, that looks cool, and you're going to touch it, but you're not supposed to touch it, because as soon as you touch it, you may break the surface tension. And once you break the surface tension, that water is dripping into your tent from that spot that you touched it, and you're probably not going to have a good night. So resist the urge to break the surface tension on your tent if it's raining out. And when you wash your hands, when we use detergents, if you washed your hands with just regular water and that's it, sometimes the surface tension's too great. These water molecules are too bound to each other. They form too big of a clump. It doesn't look like it. It looks perfectly smooth. But on a microscopic level, the water's not as diffuse as it could be. It's forming these clumps because the water has cohesion and it joins together. But if you add a little soap to the scenario, that breaks the surface tension. It lowers the surface tension, which means these water molecules don't clump together as much. And if they're not clumping together, they can get into the small cracks, which kicks out the dirt in your hands. And this water is better able to penetrate into the smaller cracks and get where it needs to go. So surface tension is due to cohesion between the water molecules at the surface of a liquid. But water molecules aren't just attracted to each other, they're actually attracted to the container too, and other materials. And that's called adhesion. So the fact that water molecules are attracted to other materials as well is called adhesion. So what happens is this water molecule isn't just attracted to the other water molecules, it's attracted to the wall, and these water molecules climb the wall a little bit. So that's why you'll see when you fill a container with water or you're measuring an amount of liquid in a small burette, it's not perfectly level with the surface. It actually forms this kind of shape like that. This is exaggerated, but the sides will be a little higher than the middle. So you have to be careful when you're measuring. This is usually called the meniscus, and it's caused by the adhesion, the attraction of water molecules to the container that it's in. This adhesive force, this adhesion force is important. It causes something called capillary action. So let me get rid of this. If you have a container with liquid, or say water, and you took another container, you put it in here like a straw, if you just stick it in, what you'll see is that because the liquid is attracted. It causes something caused by the adhesion, the attraction of water molecules to the container that it's in. This adhesive force, this adhesion force is important. It causes something called capillary action, an amount of molecules, surface small to co-liquid, but in your hands, and this water is better able to penetrate into the smaller cracks and get where it needs to go. So surface tension is due to cohesion between the water molecules at the surface of a liquid, but water molecules aren't just attracted to each other, they're actually attracted to the container too and other materials, and that's called adhesion. So the fact that water molecules are attracted to other materials as well is called adhesion. So what happens is this water molecule isn't just attracted to the other water molecules, it's attracted to the wall, and these water molecules climb the wall a little bit. So that's why you'll see when you fill a container with water or you're measuring an amount of liquid in a small burette, it's not perfectly level at the surface. It actually forms this kind of shape like that. This is exaggerated, but the sides will be a little higher than the middle. So you have to be careful when you're measuring. This is usually called the meniscus, and it's caused by the adhesion, the attraction of water molecules to the container that it's in. This adhesive force, this adhesion force is important. It causes something called capillary action. So let me get rid of this. If you have a container with liquid or say water, and you took another container, you put it in here like a straw, if you just stick it in, what you'll see is that because the liquid is attracted to the walls of this inner container, it doesn't just stay at this level, it'll rise above. It pulls this up a little bit above the surface level of the water. And if you took an even smaller diameter tube and put it in there, the smaller the tube, the greater this effect, and you'd get this water rising to an even higher level within this tube due to the adhesion to the walls of this container. And the name for this effect is capillary action, which is important in a variety of biological and non-biological examples where fluid is being aided in transport partially by the attraction to the walls of the container or the tube that it's flowing in. Venturi effect. This has to do with water or any fluid flowing through a pipe. And it turns out, let's say this water's flowing right here, minding its own business, having a good day for that matter, when it meets a constriction. What's going to happen here? Well, the water's got to keep flowing, but it's going to start flowing faster through the constricted region. And the reason is, well, there's a certain amount of fluid that's flowing through this pipe. Let's say all the fluid in this region right here, let's say this front part of the water, I mean, this whole thing's filled up, but just say this cross section of the water happened to make it from this back portion to this front portion in, I don't know, let's just say 1 second. So this entire volume moved through this section of the pipe in 1 second. Well, there's a law in physics that says that same volume's got to make it through each portion of this pipe, because if it didn't, where's it going to go? This pipe would have to be filled up, but just say this cross section of the water happened to make it from this back portion to this front portion in, I don't know, let's just say 1 second. So this entire volume moved through this section of the pipe in 1 second. Well, there's a law in physics that says that same volume's got to make it through each portion of this pipe, because if it didn't, where's it going to go? This pipe would have to break or something. This water's got to go somewhere. If that much flowed through here in 1 second, then this much has to flow through this little tiny region in 1 second. But the only way that that's possible is for the front surface, instead of just traveling from there to there in 1 second, the front surface is going to have to change its shape. But the front part of the water is going to have to travel from here to here, maybe in a quarter of a second, because all of this has got to cram through here in the same amount of time. That water's still coming behind it. There's more water coming. And the volume flow rate's got to stay the same. The volume per time flowing through one region of the pipe has got to be the same as the volume flow rate through some other region of the pipe, because this water's got to go somewhere. It doesn't just disappear in here. It's got to keep flowing. That means the important part is the water flows faster through the constricted region, sometimes much faster through the constricted region. The smaller this is compared to this original radius, the faster the fluid will flow through here. Why do we care? Well, because faster moving fluid also means lower pressure. Why does faster moving fluid mean lower pressure? Well, if we look at the Bernoulli equation, Bernoulli's equation says P1 plus rho g H1 plus 1/2 rho V1 squared equals P2 plus rho g H2 plus 1/2 rho V2 squared. Oh my goodness, this looks frightening. But look at P1. We just pick some point in the pipe. Let's just pick this point right here. Call that point 1. So all these ones, this whole side refers to that point. Let's just pick point 2 right here. All this whole side refers to that point. Now notice something. These are like basically the same height. And assume height's not really a big difference here. So let's cross out the heights. They're the same heights. We don't have to worry about that. This says that, all right, if there's some pressure at 1 and some velocity of the water at 1, you can plug those in here and get this side. And now look over here. We know the velocity at 2 is bigger. We just said that. It has to be because the volume flow rate's got to stay the same. So this speeds up in here. So this is bigger, this quantity here. But we know the whole thing equals this side. So if this term increased, that means the pressure's got to decrease so that when they add up, they get the same as this side over here. This is actually called Bernoulli's principle. Bernoulli's principle says that when a fluid speeds up, its pressure goes down. It's totally counterintuitive. We always expect the opposite. We think fast moving fluid, that's got to have a lot of pressure, but it's the exact opposite. Fast moving fluid actually has a smaller pressure, and it's due to Bernoulli's equation. And this is what causes the Venturi effect. The Venturi effect refers to the fact that if you have a tube and you want a smaller pressure region, you want the pressure to drop for some reason, which actually comes up in a lot of cases, just cause a narrow constriction in that tube. In this narrow constriction, faster moving fluid, and it'll cause a lower pressure. This is the idea behind the Venturi effect. So the Venturi effect basically says for a constriction in a pipe, you're going to get a lower pressure. While we're talking about fluid flow, we should talk about one more thing. Let me get rid of this here. Imagine you just had a brick wall with fluid flowing towards it. Maybe it's air here. So we've got some fluid flowing towards this brick wall. This seems like a really dumb example of Bernoulli's principle, but I'm going somewhere with this, so stay with me. This is flowing towards here. What's going to happen? Well, it can't go through the wall. It's got to go somewhere. Maybe this just goes up like that. And this, I'm going to go this way. It's closer to go that way. This side, and it just goes down. This is actually kind of what happens. But there'll be a portion in the middle that basically just terminates. It hits here and kind of just gets stuck. So there'll be some air right near here in the middle where it's just not moving. What if we wanted to know what the pressure was there based on the variables involved in this problem? We could use Bernoulli's equation again, pick 2 points. Let's pick this one, point 1. Let's pick this one, point 2. Use Bernoulli's equation. It says this. And again, let's say these are basically the same height. So that height is not a big factor. If these terms are the same, then we can just cross them out because we can subtract them from both sides. They're identical. Now what can we say? We know the velocity of the air at 2. It's not moving. It got stuck here. It got stagnant. And so V2 is just 0. And we get this statement that the pressure at 2, which is sometimes called the stagnation pressure. Someone call it the stagnation pressure because the air right here gets stuck and it's not moving. You might object. You might say, wait, hold on. I thought the air had to go somewhere. Well, it's all going somewhere. The point is there's some air right here that gets stuck. It gets stuck and air starts passing it by. And so what's this pressure here? Well, up here, we read it off. All these went away. P2, which is what I'm calling the stagnation pressure, got to equal P1, the pressure over here, plus 1/2 rho V1 squared, and we get this formula. You might think, why would we care about this? Who is regularly shooting air at a brick wall? People do it all the time because you can build a pretty important instrument with this called a pitot tube. And the pitot tube looks something like this. Let's get rid of that. So why would someone use this system? It's called a pitot tube. People use it to measure fluid velocity, or if you're moving through the fluid, it's a way to measure your velocity or your speed. So what happens is you've got this setup. Let's say you're in an airplane. You mount this on the airplane. You're flying through the fluid, which is the air. That means air is rushing towards this section here. Right?
All right, hold on, guys. I'll have to go to a seminar thing. Okay, my bad, guys. I was just waiting for I was just waiting to get the. I was just waiting to get the forms from the seminar, but I got them now, so we can continue. Oh, thank you, Michaela. Very nice. That's good. Yeah, maybe I'll do a video. Maybe I'll do a video tomorrow morning or something. Like, like a happy video and thanks for everyone for subscribing, something like that. Yeah, thank you. Thank you for letting me know. Yeah. Nice. Okay, let's continue. Let me clean up and let's get back to it. We ended off here, and then I had the seminar, but I got the form, so we're good. I'll be back. Faster? Then maybe. Anyways. Yeah. All right, let's continue.
Rushing past you. Let's say you're flying to the left. So notice air flying past you. A pitot tube always has this section that's facing into the wind or into the air. This air would be directed straight toward this region. And the key is, this is block about this. Who is regularly shooting air at a brick wall? People do it all the time because you can build a pretty important instrument with this called a pitot tube. And the pitot tube looks something like this. Let's get rid of that. So why would someone use this system? It's called a pitot tube. People use it to measure fluid velocity, or if you're moving through the fluid, it's a way to measure your velocity or your speed. So what happens is, you've got this setup. Let's say you're in an airplane. You mount this on the airplane. You're flying through the fluid, which is the air. That means air is rushing towards this section here, rushing past you. Let's say you're flying to the left. So notice air flying past you. A pitot tube always has this section that's facing into the wind or into the air. This air would be directed straight toward this region. And the key is, this is blocked off at the end. So there's air in here, but it can't be moving. The air in this section can't be moving all the way to the front because, I mean, where's it going to go? We just said if fluid flows in, fluid's got to flow out. There's no out here. And then there's another region. Up here, you've got a second chamber where the air flows over the top, and this is directed at a right angle to that airflow. You've got another chamber, and again, in here, fluid's not flowing. The key is, this gives you a way to determine the difference between the pressure here and the pressure there. If you had some sort of membrane in here, something dividing these two sections that could tell you the pressure differential, right? If the pressure on this side is a little bigger than the pressure on this side, then this would go outward. One of these is measuring the pressure here, and one of them is measuring the pressure there. What is it mathematically? What's the relationship? It's the one we just found right here. This is the stagnation pressure, right? The air is not moving in here. It flows straight in. We know the V is 0 right here. And so the stagnation pressure equals the pressure up here. Again, I'm assuming there's very little height difference. Let's say this is a very small device and it's not like 10 meters tall. So any height differences are minuscule. And we would just have our same equation before. This would just equal the pressure plus 1/2 rho v squared. And this is how you determine the velocity or the speed, because now we can just solve this for v. I get that v1 equals ps, the stagnation pressure, minus the pressure at 1. That whole thing times 2 divided by the density of the air, and then a square root because you have to solve for the v1. So this device lets you determine this pressure differential right here. Check. You need to know what the density of air is, and this gives you a way to determine the velocity of the fluid, or in other words, the velocity of your aircraft flying through the air.
Sense. So what you're looking at is basically a kind of mechanistic way of thinking about the heart, almost as if it's a couple of pumps with pipes attached to the pumps. And in a way, that's not a bad way to think about the heart. In fact, we're going to kind of move through this diagram. And I realize it looks a little bit scary. But once I start labeling stuff, you'll start seeing that it's actually not as bad as it seems. So let's get started in the upper part of the heart. The right atrium is right there, and the blood goes down into the right ventricle. And then on the other side, I'm going to label the last two chambers, the left atrium and the left ventricle. We're going to actually follow the path of the blood after it leaves the right ventricle. We're going to start our journey here at the right ventricle. So what's the first thing that kind of comes across? Well, blood leaves the right ventricle, goes through a valve, and after on the other side, you've got this area right here. And I've drawn it as one tube with no slit, and this is the pulmonary trunk. So blood is headed towards the lungs, going first through the trunk, and of course, after the trunk, there's a left and right. So right up here, the pulmonary arteries are next. Remember, I call them arteries because they're going away from the heart, and there are two arteries, so pulmonary arteries, left and right pulmonary arteries, and that's why you see two things here, one here, and you see one here. And those are basically tubes. So it's going from the pulmonary trunk, it's splitting into one of the two tubes. And I'm drawing the left and right lung up top, and of course, you know that the lungs are actually not going to look this way, so this is not anatomically correct, but this is not, as I said in the beginning, a bad way of thinking about it. So blood goes through the lungs and then comes out on the other side, and there, we're going to talk about left and right pulmonary veins. And actually here, I'm going to make the point that there aren't just two pulmonary veins, one for each lung. Actually, there are usually more than that. And so when I draw this too, I really want you to think of the two sides, veins coming from both sides. The actual number could be a few pulmonary veins in total. The pulmonary veins drain blood then into the left atrium, right? So now we're on the other side of the heart. And for the moment, I'm going to kind of pause the journey here. So we go from the right ventricle around to the lungs, back again in the left atrium. And this is kind of the first part of our journey. And this part of the journey is called the pulmonary circulation. I'm actually just going to write that here. Actual number on the other side, and there, we're going to talk about left and right pulmonary veins. And actually here, I'm going to make the point that there aren't just two pulmonary veins, one for each lung. Actually, there are usually more than that. And so when I draw this too, I really want you to think of the labeling stuff. You'll start seeing that it's actually not as bad as it seems. So let's get started in the upper part of the heart. The right atrium is right there, and the blood goes down into the right ventricle. And then on the other side, I'm going to label the last two chambers, the left atrium and the left ventricle. We're going to actually follow the path of blood after it leaves the right ventricle. We're going to start our journey here at the right ventricle. So what's the first thing that kind of comes across? Well, blood leaves the right ventricle, goes through a valve, and after on the other side, you've got this area right here. And I've drawn it as one tube with no slit, and this is the pulmonary trunk. So blood is headed towards the lungs, going first through the trunk, and of course, after the trunk, there's a left and right. So right up here, the pulmonary arteries are next. Remember, I call them arteries because they're going away from the heart. And there are two arteries, so pulmonary arteries, left and right pulmonary arteries. And that's why you see two things here, one here, and you see one here. And those are basically tubes. So it's going from the pulmonary trunk, it's splitting into one of the two tubes. And I'm drawing the left and right lung up top. And of course, you know that the lungs are actually not going to look this way. So this is not anatomically correct. But this is not, as I said at the beginning, a bad way of thinking about it. So blood goes through the lungs and then comes out on the other side. And there, we're going to talk about left and right pulmonary veins. And actually here, I'm going to make the point that there aren't just two pulmonary veins, one for each lung. Actually, there are usually more than that. And so when I draw this too, I really want you to just think of the two sides, veins coming from both sides. The actual number could be a few pulmonary veins in total. The pulmonary veins drain blood then into the left atrium, right? So now we're on the other side of the heart. And for the moment, I'm going to kind of pause the journey here. So we've gone from the right ventricle around to the lungs, back again in the left atrium. And this is kind of the first part of our journey. And this part of the journey is called the pulmonary circulation. I'm actually just going to write that here, pulmonary circulation. So the fact that this part is going, starting from the heart and going back to the heart is one circuit. And our heart actually has two circuits. So I want to point out the circuits one at a time. We've already kind of completed one circuit. So I'm going to just take some blue paint to indicate deoxygenated blood or blood without oxygen. I'm going to paint in how it would look. Actually, it's stopped there because of my arrows, but you can actually see now the deoxygenated blood kind of goes from the right ventricle through the pulmonary trunk, through the arteries, and into the left and right lung. And once it's there, it's going to kind of mix in with the capillaries, and it's going to start getting oxygen. And then it's going to come out on the other side in the pulmonary veins. And it's, again, stopped a little bit there, but I can fill it in. And the pulmonary veins are going to deliver that oxygenated blood to the left atrium. So what you see kind of colored in now is the pulmonary circulation. That's the first part of our circuit. But let's now keep going and now talk about the second part of the circulatory system, which is the systemic circulation. So now the journey starts with the left ventricle. So let me start there. So for the systemic circulation, I'm going to start the left ventricle, and it's going to go around to the body, right? The body is kind of the thing that's going to be receiving all of the blood. And when I say body, I really mean lots of things. I mean things like the brain, so it could be an organ, like the brain or the liver. It could also be, maybe things like bones. If you have bones in your fingers, it could be the toes. It could be any part of your body that you can think of, right? So all of these different organs and tissues are going to be getting blood from the left ventricle. It's going to be going initially through a giant vessel. This vessel, I'm going to label, say, here as the aorta. So this large vessel is the aorta. Of course, it branches and splits, and I haven't shown all the branches that come off the aorta, but there are many, many of them. It goes to the various tissues and organs, and then it comes back out on the other side. And at the end, kind of somewhere up here, it's going to go back to the right atrium. And it generally travels through two major kind of vessels. One is the inferior, and the other is the superior, meaning lower and upper. And they're both called vena cava. So superior vena cava and inferior vena cava. I'll show that here. So these are the two major veins that are bringing back blood from all the different parts of the body. And so now you've actually seen the second circulation, which all ends at the right atrium. And this is the systemic circulation. I'm going to write systemic circulation here. So now you can see that the heart is really two different systems, or let's say two different circuits rather. And the first one, the pulmonary circulation, is really kind of relying on the right ventricle as the pump. And the second one is relying on the left ventricle as the pump. And actually, now that you've seen, I can now color it in. There, it would kind of deliver all the blood to the various organs, and then the organs would use up the oxygen. So we show it kind of now going back to blue. Indicate deoxygenated blood, and it goes back to the right atrium as deoxygenated blood. So this is kind of how we sometimes see it. And again, this doesn't show you or give you an appreciation for the anatomy exactly, where things branch off and where the different names make sense. But you get a kind of overall feel for the fact that we have two different circulations, and you can see where the blood is going through the two different circuits. And when you look at this picture, you can say, well, okay, I guess you can see where all the different tissues are getting the blood. Basically, it sounds like everything is coming from the oxygenated blood coming out of the left ventricle. But some tissues always kind of trip people up or just kind of spark a question. And I'm just going to kind of try to target a couple of the tissues I think people sometimes might have questions about. And one of them, we don't really call it a tissue, but you could definitely call it a cell type. It's the RBC, and RBC just stands for red blood cell. So people sometimes wonder, if the red blood cells are carrying blood to other parts of the body, then how did they themselves get oxygen? Do they just kind of use up some of the oxygen that they're carrying, or what exactly? And to answer this question, I would have to remind you that a red blood cell basically looks a little bit like this, right, in cross section, and it doesn't have any mitochondria, no mitochondria. So it has no mitochondria. And remember, mitochondria are these tiny little organelles inside of cells that are using oxygen. So if it has no mitochondria, then it is not really using oxygen. So it's not using oxygen. And really, these cells, we call them cells, and they are in many senses of the word, but they don't really have mitochondria. They also don't have a nucleus. I mean, these are literally these amazingly designed cells that are made for the purpose of carrying around oxygen to the body, because they literally are bags of hemoglobin. So just remember, red blood cells don't really need oxygen. They simply carry it around. Another tissue or organ that makes people kind of wonder is the heart. The heart is pumping all the blood around, but does it actually get oxygen from vessels that are in the pulmonary circulation or from the systemic circulation, or what? And here, the short answer is systemic circulation. That's kind of the quick answer. And let me actually show you where the blood vessels come from. These are called coronary vessels. I'll just write the word coronary here. Coronary vessels, so coronary artery and vein. And these coronary vessels, they actually come right off the aorta here and here. So they kind of come off of the aorta right away. They're the first branches off the aorta, actually. So the first branches go and serve the heart. So it's kind of the first to get systemic circulation blood. And the veins actually drain into the spot directly into the right atrium. So there's actually a little spot right there that they drain into. So the blood from the arterial side is coming from the aorta, and on the venous side, it's actually not even dumping into the inferior or superior vena cava. Kind of a little known fact, it's going directly into the right atrium. And finally, kind of a tricky one, but the lungs. Where do the lungs get their oxygen from? And this is, I say tricky, and I can save this for last, because they're actually blood vessels. And again, don't worry so much about the anatomy in terms of like where is it coming off of exactly, but it's coming off of the systemic circulation. And you've got a vessel going to the right lung, let's say something like that. And you've got another vessel going, I'll just drop kind of going to the left lung like that. So you've got a couple of arteries that are branching off, and these are also part of the systemic circulation. And these are called the bronchial arteries. And these bronchial arteries bring then really wonderful oxygenated blood, right? These are the bronchial arteries. And you might say, well, that wasn't so difficult. I'll say bronchial vessels because there are also some veins coming off. Actually, we draw the veins down for you so you can see how those kind of end up. And these veins, they come from, of course, the right lung, and they actually end up kind of dumping in here. Can't really show blue on blue, but just trust they kind of go there. And you've got another vein from the other one, kind of following a parallel path and going into the veins as well. And so they don't necessarily directly into the inferior superior vena cava, but I just want to show that they go into the venous side on the systemic circulation. So if that was it, that'd be really simple. But actually, lungs are kind of interesting in the sense that there is a lot of mixing going on. So you've got pulmonary arteries carrying blood, you've got bronchial arteries carrying blood, and that blood mixes. And then you've got at the capillaries, you've got some blood kind of from both places, the pulmonary circulation and blood from the systemic circulation again mixing. And then on the other side, where the veins are bringing blood back to the heart, most of the blood, as it turns out, most of the blood actually goes this way into the pulmonary veins. So even though you have bronchial arteries bringing blood in, that'll be right here. You only have bronchial arteries bringing blood in. A lot of that blood ends up going into the pulmonary circulation. So that's kind of an interesting fact that not as much goes this way directly into that systemic circulation. So it's kind of a tricky thing to keep in mind that the lungs then technically really are getting blood both from the systemic circulation, but also they're kind of mixing blood, and they're mixing blood with the pulmonary circulation. We'll talk a little bit more about this in another video. I don't want you to feel like this kind of got too confusing, but I just want you to be aware that there is mixing going on in the lungs with the systemic and pulmonary circulation. It's kind of a neat organ in that sense.
Towards the heart. Let's talk a little bit. Things are drawn. Those where they and so it gets pumped through the aorta. Place, especially areas the blood artery, the blood. These are considered veins because they're. So now that we have this main distinction between arteries and veins, what are some? If you were to prick your finger, it's usually a series of capillaries that get cut, and that's why the blood would come out very, very slowly. Now, arteries are high pressure, veins are low pressure, low pressure. And one way to think about it is the artery is the blood is being pumped directly by the heart, but then have that high boost. And to appreciate the difference, the blood volume in arteries and where the rest of the blood is, about 5% is in capillaries, 5% is. I will leave you there. The big takeaway. Which means R is proportional to 1 over R to the 4th over 16, because 2 to the 4th power is 16, right? And it's in the denominator here. And so if we flip it out to the top, and I'm going to talk about an inferior vena cava, and the blood flow. We see something really, really cool, which is that. So let's say you're walking down the street, and I'm going to draw you here, and you decide to do a little experiment. You take a deep breath as you're walking, and you decide to blow out through a cardboard.
Hold on, I need to put on some eye drops. Okay.
Or 2, something like that. And let's say it's like a toilet paper roll. And so you blow out through it, and here in this toilet paper roll, the length is called L, and here there's a radius, and it's called R. And we know that toilet paper roll is, let's say, about 2 centimeters radius. That may not be exactly right, but let's just assume that. And you do this, and you find that it's so easy to do. Very easy to take one breath of air and blow it out through each cardboard 2. And so you decide to do it slightly differently. You do it again, and now you do it slightly differently. Now you go ahead and take an equal size breath, but you instead of a 2, you choose a straw. And that straw is obviously much skinnier. And you try, and you find that it's actually really hard to blow air through that straw. Not as easy as it was before. And so you find that it's much, much more difficult. And you want to figure out why. And you know that 2 was L, and this straw is the exact same length as L. And the radius now is smaller. So instead of R, the closest part time. And instead of 2 centimeters, it's about, let's say 1 centimeter. Pretty big straw still, but let's just assume that's the moment. You want to figure out why in the world is it harder with a straw. And this question posed slightly differently. It was asked actually a long time ago by a gentleman, French gentleman, by the name of Dr. Jean-Louis Marie Lossat. And I'm actually mispronouncing that a little bit, so I apologize to any of Dr. Lossat's relatives, but this is a Frenchman, and he still has a name for you. He actually lived in the 1800s, with one of the 1800s, but lived in the 1800s, and in the 1840s, he put together a set of equations that helps us answer that question that I just asked, which is about why was it more difficult in one situation than next. So he said, if you have a tube, and you're trying to get a fluid through that tube, so in this case, not air, but a fluid, but you'll see that a lot of the math is very similar. He said, if you know the length of the tube, let's call it L, this is what we did before, and if you know the viscosity, and viscosity he calls eta, ETA, this is viscosity of the fluid,
you know these things. And lastly, if you know the radius, then you can actually calculate the resistance. And these are the resistance. And I'll just call it R from now on, big R, not to confuse you with little r, which is radius, equals 8 times the length times the viscosity divided by the number pi times the radius to the fourth power. Now that might look confusing, but look at this. We actually have a lot of these values. We know the length of the two. We can probably figure out the viscosity. And all we need to do is measure the radius, and we have the resistance. So it's a pretty powerful formula, and we can actually use this to understand what happened earlier. So in this earlier example, I'm going to go back to this now. Let's take that resistance formula. So big R equals, it was 8 times L times resistance over pi times R to the fourth. And I'm just going to go ahead and replace this with resistance is proportional, therefore, to 1 over R to the fourth. And you can see why that's the case, because all of this other stuff, all this stuff, can be figured out in this example. And you can see that there's a relationship between these two things that we just drawn, R and the R. And the relationship is stated here, right? So you have, as the radius gets very, very, very big, the resistance is going to get very, very small. And in fact, it's going to happen very quickly because you're raising the radius to the fourth power. Now let me take this one step further. Let's look at the other side now. Over here, right? So you have, as the radius gets very, very, very big, the resistance is going to get very, very small. And in fact, it's going to happen very quickly because you're raising the radius to the fourth power. Now let me take this one step further. Let's look at the other side now. Over here, we have a situation where we said, we have, again, rate resistance equals 8 times the length times viscosity divided by pi. So far, it should look the same, obviously, right? And here's the big change. So instead of R, I'm going to say R prime to the fourth power. Now, what's the relationship between the two things? So we said that if R is 2 centimeters, R prime is 1 centimeter. That means that R prime equals R divided by 2. And of course, I made up these numbers, so that relationship is just for this example. And so if R prime equals R over 2, I'm going to replace that in my equation. So just as before, I'm just going to say R is now proportional to 1 over R prime to the fourth power, which means that R is proportional to 1 over R over 2 to the fourth power, which means R is proportional to 1 over R to the fourth over 16, because 2 to the fourth power is 16, right? And it's in the denominator here. And so if we flip it up to the top, we see something really, really cool, which is that it's 16 over R to the fourth. So in other words, compare the first example where you had R proportional to 1 over R to the fourth, and now you have R proportional to 16 over R to the fourth. That means that it's harder because the resistance is 16 times greater. That's remarkable. You just dropped the radius a little bit. You went from 2 centimeters to 1 centimeter, and the resistance went up 16 times, and that's why it was so hard. So now let's apply this to blood vessels. So if you now understand the idea that you have blood vessels that are greater, that's remarkable. You just dropped the radius a little bit. You went from 2 centimeters to 1 centimeter, and the resistance went up 16 times, and that's why it was so hard. So now let's apply this to blood vessels. So if you now understand the idea that you have blood vessels, and they're basically like tubes, and you can probably see where this analogy is going. There are parts of the blood vessels that are called arterioles. That's a part of the circulatory system. Arterioles. And these arterioles have a very interesting property, and that is that if you look at them closely, they're covered with smooth muscle. So all these bands of smooth muscle kind of wrap around this arteriole. And what it does is that when the smooth muscle is relaxed, let's say it's very relaxed, then you get something like this. And if it's squeezing down or tightening, or it's like constricting, then you get something like this. And you can probably guess what that's something like that. And I haven't gone to smooth muscle here, but you can still guess it's basically like this. These are wide open, relaxed, completely at ease. And these are tight, very, very tight. And that's why they're bringing the diameter and therefore the radius of the vessel, from this radius to this radius. It's just like our cardboard tube versus our straw. And so when it's relaxed, we call this vaso meaning vessel dilation. And when it's constricted, we call it same thing, vaso or vessel constriction. And the reason that we want to make this distinction is that we know, based on this example now, that when you have vasodilation, what that means for the blood is that you're going to have very low resistance. The blood can flow through with very low resistance. And when you have vasoconstriction, now you can see why. That means you're going to have high resistance. And so we owe a lot of this understanding and thinking to Dr. Fossat from the 1840s. And I'm going to talk to you about pressure, resistance, if blood continues flowing, and it goes into the capillary. And then it continues to go and get collected into a venule, which sounds a little bit like arterial on the other side, right? We've got a vein over here going inferior vena cava. The pressures, the blood pressures at different points along the system. I'm going to choose some points that I think would be interesting ones to check. So it would be good probably to check what the pressure is right at the beginning. And then maybe at all the branch points. So what the pressure is as the blood goes from the aorta to the brachial artery, maybe as it ends the brachial artery and enters the arterial, maybe the beginning of the. Now these numbers, or these pressures, can be represented as numbers, right? Like what is the millimeters of mercury that the blood is exerting on the wall at that particular point in the system? And earlier we talked about systolic versus diastolic pressure. And there we wanted to use two numbers because that's kind of the range, the upper and the lower range of pressure. But now I'm going to do it with one number. And the reason I'm using one number instead of two is that this is the average pressure over time. So the average pressure over time for me, keep in mind my blood pressure is pretty normal, somewhere around 120/80 in my arm. So the average pressure in the aorta kind of coming out would be somewhere around 95. And in the artery in the arm, probably somewhere around 90. Again, that's what you would expect, somewhere between 80 and 120. So 90 is the average because it's going to be not exactly 100 because remember, it's spending more time in diastole and relaxation than in systole. So it's going to be closer to 80 for that reason. And then if you check the pressure over here by this X, it might be something, let's say 80. And then as you cross the arterial, the pressure falls dramatically. So it's somewhere closer to 30. And then here's about 20, here's about 15, let's say 10 over here. And then at the very end, it's going to be close to 5%. So here, let me try that again, 10 and 5. And the units here are millimeters of mercury. So I should just write that pressure in millimeters of mercury. That's the units I'm talking about. So the pressure falls dramatically, right? So from 95 all the way to 5. And the heart is a pump, so it's going to instill a lot of pressure in that blood, again, pumping around and around, and that's what keeps the blood flowing in one direction. So now let me ask you a question. Let's see if we can figure this out. Let's see if we can figure out what the resistance is in all of the vessels in our body combined. So we talked about resistance before, but I don't want to pose this question, see if we can figure it out. So what is total body some relationship between radius and resistance. We talked about vessels and tubes and things like that. But let's really figure this out and make this a little bit more intuitive for us. So to do that, let's start with an equation. And this equation is really going to figure this out and make this a little bit more intuitive for us. So to do that, let's start with an equation. And this equation is really going to walk us through this puzzle. So we've got pressure, P, equals Q times R. Really easy to remember because the letters follow each other in the alphabet. And here, actually, instead of P, we put delta V, which is really change in pressure. So this is change in pressure. And a little doodle that I always keep in my mind to remember what the heck that means is if you have a little tube, the pressure at the beginning, you say start, S is for start, and the pressure at the end can be subtracted from one another. And that gives you PS minus PE equals delta V. The change in pressure is really the change from one part of the tube to the end of the tube. And that's the first part of the equation. So next we've got Q. What is Q? This is flow. And more specifically, blood flow. And this can be thought of in terms of the volume of blood over time. So let's say minutes. So how much volume, how many liters of blood, or number of minutes each side. And that's kind of a hard thing to figure out actually. But what we can figure out is that Q, the flow, will equal the stroke volume, I'll tell you what this is just after I write it. The stroke volume times the heart rate. So what that means is that basically, if you can know how much blood is in each heartbeat, so if you know the volume per heartbeat, and if you know how many beats there are per minute, then you can actually figure out the volume per minute, right? Because the beats would just cancel each other out. And it just turns out, it happens to be that I'm about 70 kilos. That's me. I'm 70 kilos. And for a 70 kilogram person, the stroke volume is about 70 milliliters. So for a 70 kilo person, you can expect about 70 milliliters per beat. And as I write this, let's say my heart rate is about 70 beats per minute. I go to 12, and so it's not too fast. So the beats cancel, as we said, and I'm left with 70 milliliters times 70 per minute. So that's about 4,900 milliliters per minute. Or about 5, so the flow is about 5 liters per minute. Okay, so I figured out the blood flow, and that was simply because I happen to know my weight, and my weight tells me the stroke volume. And I know that there's a change in pressure, we got to figure that out soon. And lastly, this last thing is resistance. And I'm just going to, I know I said it before, I just want to point out to you again, the resistance is going to be proportional to 1 over R. And so just remember that this is an important issue. R is radius, and that's the radius of the vessel. So let's figure out this equation, and let's figure out the variables in this equation, and how it's going to help us solve the question I asked you. What is the total body resistance? Okay, so if I have to figure out total body resistance, let me clear out the board. I've got, let's say, the heart. We're going to do the heart in red. And it's pumping blood out of my aorta, right? So blood is going out of the aorta. And then it's going branching here, branching here. And then it's going to branch some more, and it's going to branch some more, and you can see where this is going. It's going to keep branching. And eventually, every branch kind of collects on the venous side. All the blood is kind of filtering back in, slowly into venules and veins, and finally into a venous cava. And I should really draw this going like that. The blood is going to go back into the venous cava. So that's my system, and I got to figure out what the total body resistance is here. So if I have a system drawn out for myself, and I happen to know that here I said 95, and here I said the pressure was 5, then delta T equals 95 minus 5, which is 90. And I know that there are 5 liters of blood flowing through per minute, and that was my Q. So I could say 90 equals 5 liters per minute. Actually, let me cut back from that. Instead of 90 units, 90 millimeters of mercury equals 5 liters per minute. That was my flow. That's my Q. And I've got delta T here. And my resistance is the unknown, so I'll just leave that as R. So let's just solve for R. So I'll move my flow to the other side. So R equals here, 90 divided by 5, which is 18. And units are a little funky, but I'll just write them out anyway. Millimeters of mercury times minutes divided by 8. So this is the answer to my question. What is the total body resistance? Well, we know what the pressures are at the beginning and end of our system. And we know that the flow has to be around 5 liters per minute, because that's based on my weight and my heart rate. Therefore, the resistance must be 18 milliliters of mercury times minutes over liters. Whatever that set of units means to you, it's kind of an abstract thing. But basically, I want to demonstrate to you that this powerful equation helps us solve for what would otherwise be kind of a tricky problem to figure out.
So all bodies and systems possess a property called temperature. And most commonly, temperature is used to refer to how hot or cold something is.
All right, let's take a 10-minute. Let's take a 10-minute. The finished gas phase and finish lesson 9 is only 3. I'll do the questions later. I just want to watch the videos, and then I'll finish Anki and then add them, and then I have an idea of what we're gonna do for the next couple of days, just to kind of speed things along. I think kind of close things out. Anyways, yeah. now. cool. Hello. Hi. All right. Well, all right, guys, I have to go. Thank you for watching. See you guys later. All right, guys, let's continue. We'll hit both of them. Oh, like, I guess I want to, let's hit both lessons, and then before Anki, I'll take a shower, and we'll just run it to until, I don't know, 12 or something, I guess. Something like that, I guess. I guess. Anyways, switch this over here for a second. I got that. Yeah, feels a little better. I still want. I want to take a cold shower. I really need to take a cold shower. I'll take one after this. It's really bad. All right. Anyways, let me wash my hands.
Definition of temperature is that it's a measure. So all bodies and systems possess a property called temperature. And most commonly, temperature is used to refer to how hot or cold something is. But the real sciencey definition of temperature is that it's a measure of the average kinetic energy of the particles in a system. So I've got a system and I'm filling it with little individual particles. And if we think about this microscopically, each little particle in the system is moving in some way, whether in rotation or in a straight line or curving by kind of a combination of these means. All of these little particles are moving. And the energy of motion is called the kinetic energy. So all bodies and systems possess a property called temperature. And most commonly, temperature is used to refer to how hot or cold something is. But the real sciencey definition of temperature is that it's a measure of the average kinetic energy of the particles in a system. So I've got a system and I'm filling it with little individual particles. And if we think about this microscopically, each little particle in the system is moving in some way, whether in rotation or in a straight line, or I've got a is that a sciencey definition of temperature is that it's a measure of the average kinetic energy of the particles in a system. So I've got a system and I'm filling it with little individual particles. And if we think about this microscopically, each little particle in the system is moving in some way, whether in rotation or in a part with little individual cold something is. But the real sciencey definition of temperature is that it's a measure of the average kinetic energy of the particles in a system. So I've got a system and I'm filling it with little individual particles. And if we think about this microscopically, each little particle in the system is moving in some way, whether in rotation or in a straight line or curving by kind of a combination of these means. All of these little particles are moving. And the energy of motion is called the kinetic energy. So all of these moving particles have kinetic energy. And so the faster those little particles are moving, the greater their kinetic energy. And if each of those little particles in the system has greater kinetic energy, that means the system as a whole has a larger amount of total energy, and we would say that it has a greater temperature, because again, temperature is a measure of the average kinetic energy of those particles. And because knowing the amount of energy in a system can be really useful in chemistry and in physics, we've developed temperature scales to help us quantify or measure the amount of this value of energy. So the three scales most widely used are the Kelvin scale, the Celsius scale, and the Fahrenheit scale. So Fahrenheit scale. And for all of these scales, I'm going to draw a little thermometer. So one for Kelvin, then we have a thermometer for Celsius, and then another thermometer for the Fahrenheit scale. And the two scales used most in the physical sciences are probably the Celsius scale and the Kelvin scale. So as a point of comparison here on these thermometers, the freezing point of water occurs at 0 degrees Celsius. So we have 0 degrees Celsius, that's where water freezes. And then the boiling point of water occurs at 100 degrees Celsius. So the boiling point of water occurs at 100 degrees Celsius. That's where water turns into steam. And I'm gonna write H2O here real quick, just so we don't get confused that we're talking about the freezing and boiling point of water. Now, when we use the Kelvin scale, we find that water's freezing point is 273.15 Kelvin. And then we find that water boils at 373.15 Kelvin. So they differ fundamentally in the 0 point. The Celsius and Kelvin scales differ in the 0 points that they use, but between water's freezing point and water's boiling point, we have a span of 100 temperature units for both scales. So although they differ in the 0 points that they use the same size unit or the same magnitude of unit to measure the temperature. So converting then between the two scales only really requires that we make an adjustment for the two different 0 points. And this is what I mean. If we want to know the temperature in Kelvin, all we need to do is take the temperature in Celsius and add 273.15 degree units to it. So if we want to know the temperature in Kelvin for the freezing point of water, we take the temperature in Celsius, which would be 0, and we add 273.15 units to it, and that would give us 273.15 Kelvin. Now, if we want to flip that, and if we want to find the temperature in Celsius from Kelvin, all we have to do is take the Kelvin figure and subtract 273.15 to it, or to subtract 273.15 from it, excuse me. And so we would see that 373.15 Kelvin minus 273.15 would give us 100 degrees Celsius. So just as another example, let's convert 300 Kelvin to Celsius. And to start, since we're looking for Celsius, we'll take that Kelvin value and we'll subtract 273.15 from it. And that's going to give us 26.85 degrees Celsius. So 26.85 degrees Celsius is the same thing as 300 Kelvin. And I just want to point out really quickly that I'm only using the degree symbol here for Celsius. And I'm doing that intentionally. We don't need this symbol with Kelvin scale because instead of calling the temperature units degrees, we just call them Kelvin. So the only thing we need is an uppercase K. Now, converting between the Celsius and Fahrenheit scales is a little bit more complicated. You see, in Fahrenheit, water freezes at 32 degrees Fahrenheit. So 32 degrees Fahrenheit, and water boils at 212 degrees Fahrenheit. So 212. And this gives us a span between the freezing point and the boiling point of water of 180 degree units. So we're going to need to consider two different adjustments here. One for degree size, because the units have a different magnitude. The same value or the same span of temperature is 100 units in Celsius and 180 units in Fahrenheit. And we're also going to need to account for the two different 0 points, 0 degrees Celsius for freezing and 32 degrees Fahrenheit for the freezing point of water. So first we can say that 180 degrees Fahrenheit is equal to 100 degrees Celsius. And again, we can say this because both of these magnitudes refer to the same change in total energy. And so if we write this as a ratio, we have 180 over 100, which just reduces down to 9 over 5. So the ratio of Fahrenheit to Celsius is 9 to 5. Now we need to think about the two different 0 points. And because 32 degrees Fahrenheit is equal to 0 degrees Celsius, we can find the Celsius temperature if we take the temperature in Fahrenheit and we subtract 32 degrees from it. And this makes sense because 32 degrees Fahrenheit minus 32 degrees Fahrenheit will give us 0 degrees Celsius. And now we just need to apply the unit ratio. So just like any dimensional analysis problem, we need to cancel out the degrees Fahrenheit. So if we put the degrees Fahrenheit on the bottom here, so 9 degrees Fahrenheit, we can cancel out the Fahrenheit, leaving us with just degrees Celsius. So to find the temperature in Celsius, we take the temperature in Fahrenheit, subtract 32 from it, and multiply it by a ratio of 5 to 9. And then we can also manipulate this formula if we want to start with Celsius. So all we have to do is solve for the temperature in Fahrenheit. And so to start, we would divide both sides by 5 over 9, or that's the same thing as multiplying by the reciprocal. So, and then to finish it off, we would just add 32. So plus 32 is equal to the temperature in Fahrenheit. So now, if we want to start with temperature in Celsius, we can move to temperature in Fahrenheit, or we could start with temperature in Fahrenheit and move to temperature in Celsius. And so to practice this, let's go from Celsius to Fahrenheit. And it turns out that these temperature scales actually cross paths at a temperature, which is kind of a fun fact. So if we plug in -40, let's go from -40 degrees Celsius to Fahrenheit, we'll find that TF is equal to negative 40 times 9/5 plus 32. And so we can reduce this term here. So 5 and negative 8, or 5 and negative 40 reduces to negative 8. So negative 8 times 9 plus 32. That's negative 72 plus 32. So the temperature in Fahrenheit would equal negative 40 as well. So negative 40 degrees Celsius is the same thing as saying negative 40 degrees Fahrenheit. That's kind of just a fun fact. And another observation from this little factoid is that Celsius and Fahrenheit scales can both have negative or positive values. We see that both can be negative 40. So these can both have negative values. And that's actually a point where they differ from the Kelvin scale. The Kelvin scale can only have a positive value. And it turns out that the absolute coldest temperature is 0 Kelvin. So 0 Kelvin is absolute 0. And the reason we can't get any colder is that at this point, no particles would have any kinetic energy. And so that means no motion at all. We said that temperature is a measure of the kinetic energy, and the coldest that you can get, that absolute 0. And the reason we can't get any colder is that at this point, no particles would have any kinetic energy. And so that means no motion at all. We said that temperature is a measure of the kinetic energy, and the coldest that you can get is no kinetic energy whatsoever. And it turns out that the laws of physics, specifically the uncertainty principle, just don't allow for this. So we can get close, like within a billionth of a Kelvin, but we can't get all the way there. And because Kelvin scale always has a positive value, it becomes a little handier in various formulas. And so it's used as the standard, the SI unit for temperature. So I'll show you in future videos why absolute zero happens at negative 273.15 degrees Celsius. But I'm starting to run out of time in this one, so I'm going to have to save it for later. And I'll talk about that with standard, or as why absolute zero happens at negative 273.15 degrees Celsius. But I'm starting to run out of time in this one, so I'm going to have to save it for later. And I'll talk about that with Charles' law in the future. We typically consider matter to exist in 3 distinct states. We've got solids, we've got liquids, and we've got gases. And of those 3, probably the least often considered are gases. And maybe that's because we can't often see or hold gases too well. But it doesn't mean that gases aren't important. In fact, the very air that you're breathing right now is a gas. So at a macroscopic kind of big picture level, the gas phase refers to a system in which the molecules don't have a definite shape or volume. So I've got kind of a cloud of gas here, and it doesn't have a shape or a volume to it. And at the nitty-gritty kind of microscopic level, we're talking about a substance with molecules that are freely moving through space. So these particles are moving kind of freely through space. And this means that the energy of their motion, which is their kinetic energy, is greater than the potential energy of the intermolecular forces that might hold these molecules together as a solid. Now, one of the more intuitive properties of a gas is that it exerts, these particles are moving kind of freely through space. And this means that the energy of their motion, which is their kinetic energy, is greater than the potential energy of the intermolecular forces that might hold these molecules together as a solid. Now, one of the more intuitive properties of a gas is that it exerts pressure on its surroundings. So a gas exerts pressure. The potential energy of the intermolecular forces, kinetic energy, is greater than the potential energy of the intermolecular forces that might hold these molecules together as a solid. Now, one of the more intuitive properties of a gas is that it exerts pressure on its surroundings. So a gas exerts pressure on the surroundings. And for example, when you inflate a balloon, the gas inside exerts a pressure on the elastic sides, making them kind of grow taut and then eventually causing them to expand. And so what is this pressure that's causing the gas in the balloon to expand? Well, pressure is actually a measure of force per unit area. So what's actually going on here is that the little particles in here are moving around the container. So they have a velocity. They're moving around the container. And when they collide against the container, they exert a force on the area of collision. And while one little particle collision might not have a huge amount of pressure, when you think about the huge amount of particles and the huge number of collisions, we pretty easily get enough pressure to fill the balloon. And the neat thing about balloons is we typically don't just fill them up a little bit, we can fill them up a lot. And the more we fill them up, the tauter the sides get, indicating that they have more pressure. So what might cause the pressure to increase? Well, according to our little pressure formula here, pressure is directly proportional to the force. So let's think about what would cause the force to increase. Well, we know that force is equal to the mass times acceleration. So if we increase the magnitude of the acceleration, we can increase the force, because force and acceleration are also directly proportional. That means if we have a greater change in velocity, because that's what acceleration is, it's a change in velocity. So if we have a greater change in velocity during the collision, we can increase the force. And that means that the faster our little particles are moving, the greater the force, and thus the greater the pressure. And if you remember from our last video, we said that temperature was a measure of the average kinetic energy of the particles. So really what we're saying is that when we increase the temperature, we're increasing the pressure that the gas exerts. So what else might cause the pressure to increase? Well, if the total pressure is the sum of those little individual collisions, more collisions would mean more pressure. We're increasing the pressure that the gas exerts. So what else might cause the pressure to increase? Well, if the total pressure is the sum of those little individual collisions, more collision. Well, if the total pressure is the sum of those little individual collisions, more collisions would mean more pressure. But how do we increase the number of collisions? One method might be to add more particles, because more particles means more collisions. So more moles of gas, remember that moles is simply referring to the number of particles. More moles of gas means more pressure. Now we could also increase the frequency of these collisions by making the container smaller. Because the particles would have least the frequency of these collisions by making the container smaller, because the particles would have less space to move around and would therefore hit the sides of the container more frequently. So if we decrease the volume, if we decrease the space of the container, we're going to increase the pressure. So we can change the pressure of a gas, but how do we measure those changes? Well, a long time ago in 1643, a former student of Galileo named Evangelista Torricelli, Torricelli, asked the same question while he was trying to measure the changing pressure of the gas in our atmosphere. And he solved the problem by inventing the Torricellian barometer. And barometer is a device that measures pressure. And so he took a glass tube and he filled it up with mercury. So he took a glass tube and he filled it up with mercury. And he quickly flipped it over. He flipped the tube over and he stuck the open end into an open dish of mercury. So he stuck the tube into an open dish of mercury, open and down. And interestingly enough, most of the mercury stayed in the tube. And the mercury stayed in the tube even though it was trying to flow out, because as it tries to flow out, it exerts a pressure on the mercury in the dish, which then causes the mercury in the dish to push upward against the air. And when the pressure of the rising mercury, Torricelli asked the same question while he was trying to measure the changing pressure of the gas in our atmosphere. And he solved the problem by inventing the Torricellian barometer. And barometer is a device that measures pressure. And so he took a glass tube and he filled it up with mercury. So he took a glass tube and he filled it up with mercury. And he quickly flipped it over. He flipped the tube over and he stuck the open end into an open dish of mercury.
What is an open dish? Oh, is that? Okay. Okay. An open dish of mercury. Okay.
So he stuck the tube into an open dish of mercury, open and down. And interestingly enough, most of the mercury stayed in the tube. And the mercury stayed in the tube even though it was trying to flow out, because as it tries to flow out, it exerts a pressure on the mercury in the dish, which then causes the mercury in the dish to push upward against the air. And when the pressure of the rising mercury meets the pressure of the atmosphere pushing down on the liquid surface, the mercury that's in the tube, it can't flow anymore. So the pressure in the atmosphere traps some of the mercury inside the tube. And we see that at sea level, the height of the mercury that's left in the column is about 760 millimeters. Now, if we were to measure the height of the column on top of a giant mountain, the column would be shorter because there isn't as much air pushing down on the open liquid. So more mercury from the column could escape. In fact, on the ski slopes of Breckenridge, Colorado, the height of the column would only...
Breckenridge, Colorado, that was specific. Breckenridge, Colorado. Ooh. That looks kind of nice. Look at that. Look at that. I was feeling that might be where the speaker's from, or it's where he goes for filming. Right, it's cut.
Maybe about 520 millimeters. So with less weight of the atmosphere pushing down on the surface of the mercury in the dish, more can escape, so that the amount in the column is shorter. And in order to get a baseline for comparison, we say that the pressure of the atmosphere at sea level is 1 standard atmosphere, or 1 ATM. And because a lot of manometers, which are kind of generic devices that measure pressure, use mercury, pressure is often measured in millimeters of mercury, which we know that 1 atmosphere, because it's at sea level, would equal 760 millimeters of mercury. And in honor of Torricelli, this millimeters of mercury unit is often called a torr. So 1 atmosphere equals 760 millimeters of mercury, which equals 760 torr. Now, because pressure is a measure of force per area, and the SI unit for force is the Newton, and the SI unit for area is the square meter, we have another unit of pressure, which is the Newton per square meter, and we call that the Pascal. But if we measure the pressure of the atmosphere at sea level in Pascal, we get 1 atmosphere is equal to 101,325 pascals. And so it's worth quickly mentioning pascals because it might be a unit of pressure that allows us to translate into other standard units, but mostly because this number is annoyingly large. We typically measure pressure in atmosphere or torr, especially when we're dealing with the pressure of gases.
Cool. Sounds good, my dude. Oh. It's okay.
I'm going to make a barometer. And what I have here is a glass tube that's about 800 millimeters long. And I've filled it with mercury almost to the top. And I'm going to finish filling it so that I get filled all the way to the very top. And then I'm going to put my finger over the end and I'm going to invert it into the mercury. I'm going to set it here and use our clamp to hold it. Now, what's keeping this mercury column so high? It's that atmospheric pressure pushing down on the mercury, pushing this up. Now let's see how tall our column is. 744 millimeters. It doesn't matter what size the diameter of our tube is, as long as it's relatively small. You can see this one's really small. I have another one that's almost twice the diameter of this one. But you can see that the level is the same in both tubes. What we're going to do is compare this crooked barometer to the barometer that we already have. And notice it rises to the same level.
Oh, that's a nice video. the only video I needed, which was a real mercury barometer. Okay.
Okay, in our last video, we talked about gas pressure, and we got on that subject by making some observations about the air that's inside of a balloon. So I've got a red balloon, and I'll give it a white string. The balloon gets a string, and then getting back to the observations that we're talking about. For example, we said that pressure, and the pressure inside the balloon, was really a measure of the force attributed to all the gas particles colliding with the sides of the balloon walls. So we've got our particles and they're colliding against the sides of our balloon. And given that temperature is a measure of the energy of those particles in motion, we said that increased temperature would mean increased pressure. Because if you think about it, all those particles would be moving faster with greater temperature. And just like a speeding car would crash into a wall with more force, these little particles, once they get bumpy, they exert more force and increase the pressure. So written mathematically, we would say that pressure and temperature are directly related. As the temperature is increased, so is the pressure. Now we also saw that as volume goes down, the pressure goes up. And again, this makes sense because with less space to move around, the particles will have more collisions with the wall, so pressure will increase. And again, written mathematically, this means that pressure they get bumpy and they exert more force and increase the pressure. So written mathematically, we would say that pressure and temperature are directly related. As the temperature is increased, so is the pressure. Now we also saw that as volume goes down, the pressure goes up. And again, this makes sense because with less space to move around, the particles will have more collisions with the wall, so pressure will increase. And again, written mathematically, this means that pressure is inversely related to volume. So pressure is related to the inverse of volume. Because we see that as the volume is decreased, the pressure is increased. And then we also showed that increasing the number of moles of gas would increase the pressure, because moles are just a measure of the number of particles. So if we have more particles, we have more collisions. So again, pressure is directly proportional to moles, and N is the symbol for moles. Now, based on these empirical observations, which means observations that we can actually see as opposed to just theory, we have the composite formula. If we put them together, we see that pressure is directly related to the moles and the temperature, and inversely related to volume. And so we have this composite formula. P is directly related to NT over V. And we can make this composite formula an equation if we add a constant. And we could call the constant anything, but we'll call it R. And that'll give us P is equal to R times, and that's our constant, times NT over V. And so if we multiply both sides by V and do just a little bit of rearranging, we're going to get a pretty important equation called the ideal gas equation, which is PV is equal to nRT. So PV equals nRT, and we call this the ideal gas equation. So ideal gas equation. And if you're like me, you're probably immediately curious about what that blue R is. And don't worry, I'm going to show you how we derive that in the next video. But for now, I just want you to enjoy how profound this equation is, and think about what we can do with it. For example, if we know the pressure and the volume, and we know the temperature, we can use this formula to find the number of particles that are in the system. And if we know the number of particles and we know the volume and the temperature, we can find the pressure. And if we know the number of particles and we know the volume and we know the pressure, then we'd be able to solve for the temperature. And it's pretty incredible. And this is true for any ideal gas. So the next kind of obvious question is, what's an ideal gas? Well, an ideal gas is one that obeys three conditions. The first condition is that the molecules can't exhibit any intermolecular forces. So no intermolecular forces. And we make this condition because if there were intermolecular forces, it would interfere with our assumption that all of our kinetic energy is completely directed to the pressure. So that's our first condition. And the second condition is that the molecules occupy no microscopic volume. In other words, the molecules are point masses and have no volume. And we make this condition because in our equation here, moles and volume are directly related. N is directly related to V. But if our particles take up space, then as they're added, the container's volume would actually go down instead of going up. But the particles are extremely tiny, so kind of assuming they're point masses isn't that far-fetched. And it allows our equation to make sense. So this is an ideal gas, no volume. Now the third condition is that all collisions are perfectly elastic. So collisions are perfectly elastic. Because again, we need to assume that none of our kinetic energy is lost in the collisions of these particles. So we make these three conditions, and while no gases are actually ideal, the ideal gas equation does get us some pretty close approximations, and it helps us answer lots of questions, especially those related to kind of the before and after conditions when we're changing some of these values for a gas. So next up, I'm going to explain a little bit more about the ideal gas constant, and we'll kind of dig into this R value, and then we're going to move forward with some specifics about the ideal gas equation. All right, so we just put together an equation based off some basic observations of gas, and we called it the ideal gas equation, or PV equals nRT. And for the most part, the equation
Whoops.
All right, so we just put together an equation based off some basic observations of gas, and we called it the ideal gas equation, or PV equals nRT. And for the most part, the equation is pretty intuitive, but I remember that when I was learning it for the first time, the part that confused me the most was this constant value, R. So that's what I want to try to clear up for you now. So for starters, R is a constant. And what that means is that as the rest of the variables change with whatever situation we're looking at, the R value is going to stay the same. So let me show you what I'm talking about. Let's isolate R. So when we divide both sides by the moles and the temperature, we're going to get R is equal to PV over NT, which means that for any ideal gas, if you multiply the pressure and the volume and you divide that product by the number of moles and by the temperature in the system, you're going to get the same number. Again, for any ideal gas, you'll always get the value R. So I'm going to show you how this works. But first, I need to make sure that we're on the same page about a couple different things. First, I need you to know that when I say STP, I mean standard temperature and pressure. And the standard temperature is 273 Kelvin, which is the same thing as 0 degrees Celsius. And the standard pressure is 1 atmosphere. So standard temperature and pressure is just kind of a nice theoretical condition that we can perform kind of situational experiments with. And so the second thing that I need to clarify is that we find experimentally that for any ideal gas, 1 mole of gas takes up a volume of approximately 22.4 liters. And we're going to use these conditions to find the ideal gas constant. So let's start with R equals P. This can be a theoretical condition that we can perform kind of situation.
Hold on. Don't look at me. Stop looking at me. Go back to studying.
Experiments with. And so the second thing that I need to clarify is that we find experimentally that for any ideal gas, 1 mole of gas takes up a volume of approximately 22.4 liters. And we're going to use these conditions to find a condition that we can perform kind of situational experiments with. And so the second thing that I need to clarify is that we find experimentally that for any ideal gas, 1 mole of gas takes up a volume of approximately 22.4 liters. And we're going to use these conditions to find the ideal gas constant. So let's start with R equals PV over NT. And for our conditions, we're going to talk about 1 mole at standard temperature and pressure. So for our pressure, we have 1 atmosphere, and then we have 1 mole. And we know that 1 mole is 22.4 liters, so that's our volume. And again, at standard temperature and pressure, we're talking about 273 Kelvin. And this should equal R. So if we solve this out, our 1's are going to cancel, and we really just need to divide 22.4 by 273.
PV V times T over N times T.
And that's going to give us 0.0821, and then our units are going to be atmospheres times liters, so atmospheres times liters, divided by moles times Kelvin. So the constant R is equal to 0.0821 atmospheres times liters divided by moles Kelvin. So this is the ideal gas constant that's going to be the same for all ideal gases as long as we're dealing with pressure in atmospheres and volume in liters. And it's probably the one most often used in general chemistry. But and I mentioned this earlier, sometimes we deal with pressure in a unit called a Pascal, and we deal with volume in cubic meters. And we use both of these because they're both based off of SI units. And so we might have another value for R, which looks like this. We're still going to start with R equals PV over NT. And we're still going to use standard temperature and pressure, but for our standard pressure, instead of using atmospheres, we're going to use pascals. And so 1 atmosphere is equal to 101,325 pascals. So 101,325 pascals is going to be our pressure. And we're still going to use 1 mole of gas. But instead of measuring the volume of 1 mole in liters, instead of saying that it's equal to 22.4 liters, I want to do it in cubic meters because that's another SI unit. So 1 cubic meter is equal to 1,000 liters. And this means that if we take 22.4 liters and we do a dimensional analysis, we're going to get 0.0224 meters cubed. And so that's the value that we're going to use in our formula, because we're still talking about 1 mole, so 0.0224. And then last but not least, we're still talking about standard temperature and pressure, which in Kelvin, the temperature would be 273. So we have our pressure, we have our volume, we have our moles, and we have our temperature. And so if we run this through a dimensional analysis to see if we can cancel any units, we would start with 101,325 pascals. But keep in mind that a pascal is the same thing as saying a Newton per meter squared, because it's a SI unit of pressure. So we'd have 101,325 newtons per meter squared. And then we would take our volume, and that's 0.0224 meters cubed. And so we would put that in there, and our meters, most of our meters would cancel. 2 of the meters on top and 2 of the meters on the bottom, leaving us with just a meter on top. And then we would add in a division by 1 mole, because we're dividing by 1 mole, and we'll put that on the bottom, and then we'll finish it off by putting 273 Kelvin on the bottom. And so if we simplify this down, we'd say that 101,325 times 0.0224 divided by 273, and that would give us a value of R equals 8.314 Newton meters per mole Kelvin. And we could simplify the units just a tick more, because Newton meters are the same thing as joules. So we could just insert a joule, and we'd have joules per mole Kelvin. Now, to be sure, the constants look different here, but keep in mind that the only thing changing are the units. The values here are still the same, and it's always the same for any ideal gas. So for any ideal gas system, the product of the pressure and the volume divided by the number of moles and the temperature is equal to R, which might look like 8.21 times 10 to the negative 2 atmosphere liters per mole Kelvin, or it might look like 8.314 joules per mole Kelvin. But again, this is the same value. So think about what this means. If R is constant, then R is equal to PV over NT for the initial state of a gas, so for the initial state of a gas, but R is also equal to PV over NT for the final state of a gas, so for a final state of gas. And this is true because PV over NT always equals R for any ideal gas. And so what we're really saying here is that the initial PV over NT is equal to gas for the initial state of a gas, so for the initial state of a gas, but R is also equal to PV over NT for the final state of a gas, so for a final state of gas. And this is true because PV over NT always equals R for any ideal gas. And so what we're really saying here is that the initial PV over NT is equal to the final PV over NT, which opens up all sorts of neat kind of predictive possibilities. Equals R for any ideal for the initial state of a gas, but R is also equal to PV over NT for the final state of a gas, so for a final state of gas. And this is true because PV over NT always equals R for any ideal gas. And so what we're a final state of gas. And this is true because PV over NT always equals R for any ideal gas, initial state of a gas, so for a final state of gas. And this is true because PV over NT always equals R for any ideal gas. And so what we're really saying here is that the initial PV over NT is equal to the final PV over NT, which opens up all sorts of neat kind of predictive possibilities. Final NT is equal to the final PV over NT, which opens. So what we're really saying here is that the initial PV over NT is equal to the final PV over NT, uncertainty, which opens up all sorts of neat kind of predictive possibilities, say if we were to change one of the variables. And we're going to explore these possibilities in the next few videos.
Robert Hooke.
Robert Boyle was an
Robert Boyle.
Irish scientist.
Robert Hooke. Robert Hooke. It's a different Robert. It's a different Robert.
In the 1600s, and it's actually from his experiments that we get Boyle. Robert Boyle was an Irish scientist in the 1600s, and it's actually from his experiments that we. Robert Boyle was an Irish scientist in the 1600s, and it's actually from his experiments that we get Boyle's law, which actually preceded the ideal gas equation, and we've already shown that. But we're going to work backwards, and we'll use Boyle's law to prove part of the ideal gas equation, and we get a little bit of history. Boyle was an Irish scientist in the 1600s, and it's actually from his experiments that we get Boyle's law, which actually preceded the ideal gas equation, and we've already shown that. But we're going to work backwards, and we'll use Boyle's law to prove part of the ideal gas equation, and we get a little bit of history along the way, which is always fun. So Boyle was experimenting with gases, and he had a big J tube set up in the entrance of his house, which I'm sure his wife was thrilled about. And so he trapped some gas in that J tube, and he filled the bottom of the tube with a little bit of mercury, which trapped that gas on the closed side because mercury is a pretty dense liquid. And so he trapped some gas in that J tube, and he filled the bottom of the tube with a little bit of mercury, which trapped that gas on the closed side because mercury is a pretty dense liquid, and gas has a hard time kind of moving through it. So it trapped a little bit of that gas on the other side. And so this left the open side exposed to the atmosphere here, so that you have the pressure of the gas on one side and the pressure of the atmosphere on the other. And we know that they're pressing down with the same amount of pressure because as he started, the height of the mercury was the same on both sides. Now things got really interesting when he added a bit more mercury because now the two levels didn't equalize. Instead, they were offset. And what this meant was that the trapped gas pressure over here was greater than the atmospheric pressure, such that the gas pressure was equal to the atmospheric pressure plus the fluid pressure of the height difference. And you can think that the gas is pushing down on this part of the mercury with the same force or with the same pressure as the atmosphere pushing down over here, plus this bit of fluid over here pushing down. Now, he added a bit more mercury, which compressed the gas even more, making its volume less, and he found that there was an even greater offset in the two fluid heights. And he correctly took this to mean that the gas was exerting even more pressure because now the gas pressure is equal to the atmospheric pressure plus even more fluid height. And so Robert Boyle plotted this data, and these are the values that he got in the middle of the 17th century. He plotted the volume in cubic inches, and he plotted the pressure in inches of mercury, and he was measuring that height difference for the pressure.
Okay, hold on. Hold on. Just give me like some time. I want to try to understand something from before, and then also I'm trying to understand this a little better.
And so this left the open side exposed to the atmosphere here, so that you have the pressure of the gas on one side and the pressure of the atmosphere on the other. And we know that they're pressing down with the same amount of pressure because as he started, the height of the mercury was the same on both sides. Now things got really interesting when he added a bit more mercury because now the two levels didn't equalize. Instead, they were offset. And what this meant was that the trapped gas pressure over here was greater than the atmospheric pressure, such that the gas pressure was equal to the atmospheric pressure plus the fluid pressure of the height difference. And you can think that the gas is pushing down on this part of the mercury with the same force or with the same pressure as the atmosphere pushing down over here, plus this bit of fluid over here pushing down. Now, he added a bit more mercury, which compressed.
Okay. Yeah. Okay. That's what you said. Okay. Yeah. Okay. Sure. Then what about this one? One, two, three, four, four. That's the other ones, huh? I think there's three. It's like 10 something. We should go eat something after this one, though. Still waiting to hear back from the shadow. I should email him again tomorrow. Yeah.
The gas even more, making its volume less, and he found that there was an even greater offset in the two fluid heights. And he correctly took this to mean that the gas was exerting even more pressure, because now the gas pressure is equal to the atmospheric pressure plus even more fluid height. And so Robert Boyle plotted this data, and these are the values that he got in the middle of the 17th century. He plotted
You know,
the volume in cubic inches, and he plotted the pressure in inches of mercury, and he was measuring that height difference for the pressure. And so starting off, his volume was 117.5 cubic inches, and his pressure was 12 inches of mercury. And as he filled the J tube with a little bit more mercury, he had a volume of 87.2 and a pressure of 16 inches of mercury. And as he continued to fill it, he got a volume of 70.7 with a pressure of 20 inches, and continued for a volume of 58.8 and a pressure of 24 inches, and continued and got 44.2 and 32. And as he kept going, he got 35.3 cubic inches and 40 inches of mercury. And then the last value was 29.1 inches of mercury after that's the volume that he had compressed it down to, and 48 inches of mercury for the pressure. And so what he did is he plotted this data, and he graphed pressure as a function of volume. So he had a graph with pressure as a function of volume. And if we look at our pressure, about the highest it gets is 48 inches. So we'll make the top 50, and the middle part we can say is 25 as a kind of benchmark. And if you look at volume, the highest we have is 117. So we'll make it 100, and we'll go a little bit over, and we can kind of fill in our graph. So 50, 25, and 75 cubic inches for volume. And so we see that when our volume is 117.5, our pressure is 12. So that'd be right about here. And we see that as our volume is 87.2, our pressure goes up a little bit to 16. And when we have our volume is 70.7, our pressure is about 20. So that'd be about right there. And when our volume is just about 60. Here we have a volume of 20, or I'm sorry, pressure of 24. And then as our volume goes to .2, we have 32-ish, that'd be about right there. And then 35.3 for the volume is about 40 for the pressure. And then right under a pressure of 58, our volume would be about 29, so about right there. And so what we have when we plot pressure as a function of volume is we have a hyperbola. And what we see is that as the volume drops by half from about 50 to 100, the pressure essentially doubles. And as we go from 50 to 25 for the volume, we go from 25 to 50 for the pressure about. So we have an inverse relationship for the pressure and the volume. So if we graph volume, then as a function of the inverse of pressure, we get this graph. We've got volume as a function of the inverse of pressure. So we're going to need the inverse values of all of our pressure. So 1 over 12, the inverse of 12 would be 0.08, and 1 over 16 for the inverse of 16 would be about 0.0625. And if we continue finding the inverse values of these pressures, we would get 0.05 for 20. Then 24 would be 0.042 about, and then 1 over 32 would be 0.03125, and 40 would be 0.0251 divided by 40 is 0.025, and then 1 over 48 is 0.0208. And so we can populate our graph with these values, and about the highest inverse pressure value we have is 0.08, and about the lowest is 0.02, so we can kind of fill that in here. And we're still working with the same values for volume. So the highest is a little bit over 100, and then we can put in 50 and 25 and 75. So when our volume is 117.5 cubic inches, the inverse pressure would be about 0.08. And then as we go down, 87.2 would be 0.0625. And 70.7 would be 0.05 right in the middle here. And then 58.8, just about 60 would be 0.042. And 44.2 would be 0.03125. and then 35.3 would be 0.025, and 29.1 would be 0.0208. And this isn't a perfectly clean graph, but we do see that when we graph volume as a function of the inverse of pressure, we get a straight line. And if we write this straight line graph as an equation, it would be y is equal to mx plus b. That's the equation for this graph, where m is our slope and b is our y-intercept. But our y-intercept here is 0, so all we really need is y is equal to mx. Well, in our graph, our y value is our volume, and our x value is the inverse of our pressure. So let's fill that in here. If we call our slope k instead of m, if we just use a different letter, then we'll get v is equal to k times 1 over p. And multiplying both sides by p would give us PV is equal to K. Or in other words, the product of the volume and the pressure for a gas is a constant value, just like we see in the ideal gas equation. So let's test this out by going back to those original values that Robert Boyle plotted. If we measure the product of the pressure and the volume here, we'll see that 117 times 12 is just about 1,400, and 87 times 16 is just about 1,400. And in fact, all of these volumes multiplied by the pressure, the product is always almost exactly 1,400. And so one great application of this concept is that if the number of moles and the temperature of an ideal gas are constant, then the initial product of P and B will equal the final product of P and B. So PF and VF for final. And so let's try to use this in an example. If the pressure of a gas in a 1.25 liter container is initially 0.872 atmospheres, what is the pressure if the volume of the container is increased to 1.5 liters, assuming that the temperature doesn't change? And we know that if this is a closed container, the number of particles isn't going to change. So our moles are also constant. And so let's use this idea that P1V1 is equal to P2V2. And our initial pressure is 0.872 atmospheres, and our initial volume is 1.25 liters. And we're looking for the final pressure when the final volume is 1.5 liters. And so the first thing that we're going to need to do is divide both sides by 1.5 liters to isolate our final pressure. And so on this side, we completely cancel out 1.5 liters. And on this side, we cancel out our units of liters, and we get 0.872 times 1.25 divided by 1.5. Then we'll retain our unit of atmosphere here. And that'll give us our final pressure, which happens to be 0.727 atmospheres. And just kind of as a final kind of common sense check, this result follows Boyle's law because we increased the volume from 1.25 to 1.5, and so we decreased the pressure from 0.872 to 0.727.
Okay. Sure. Charles.
Okay, so we just finished talking about Boyle's law and the experiments that led to the PV part of the ideal gas equation. And now I want to talk about the experiments that led to the V equals T part of the equation. So about 100 years after Robert Boyle, there came a French physicist named Jacques Charlet. And if I didn't look up the pronunciation for this man's name, I probably would have said Jacques Charles, but it's Jacques Charlet. And this French physicist also liked experimenting with gas. And actually turns out he was the first person to fill up a hot air balloon with hydrogen gas and fly solo. But in Jacques' experiments with gas and temperature, he found that if you heat a gas in a closed container, say like a piston, so I've got...
Hold on. I need to use the bathroom. Yeah. So this week, hopefully, I find out my dates for BMT. I need a lot of stuff. Fall in line. Fall in line.
The experiments that led to the V equals T part of the equation. So about 100 years after Robert Boyle, there came a French physicist named Jacques Charlet. And if I didn't look up the pronunciation for this man's name, I probably would have said Jacques Charles, but it's Jacques Charlet. And this French physicist also liked experimenting with gas. And actually turns out
Oui, I surrender.
he was the first person to fill up a hot air balloon with hydrogen gas and fly solo. But in Jacques' experiments with gas and temperature, he found that if you heat a gas in a closed container, say like a piston, so I've got a piston here and I'll fill it with gas, it'll be green gas. And this piston will be under constant pressure because, and actually turns out he was the first person to fill up a hot air balloon with hydrogen gas and fly solo. But in Jacques' experiments with gas and temperature, he found that if you heat a gas in a closed container, say like a piston, so I've got a piston here and I'll fill it with gas, it'll be green gas. And this piston will be under constant pressure because as the atmosphere is pushing down on top of the piston, then the pressure of the gas pushing up is going to equal the atmosphere. But under constant pressure with the same amount of particles as you heat this piston, so let me apply some heat here, and what we'll see is that the volume of the gas will also increase. So if I showed the same piston after the heat was applied, we'd see that the gas was taking up more volume, even though there's the same number of particles here. We still have 6 green particles of gas. So this is what the piston would look like after the heat was applied. And so as you heat a system of gas, the volume will also increase. And in fact, the volume increases directly with the temperature, or the volume increases proportionally to the increase in temperature. So I've got a piston here and I'll fill it with gas, it'll be green gas. And this piston will be under constant pressure because as the atmosphere is pushing down on top of the piston, then the pressure of the gas pushing up is going to equal the atmosphere. But under constant pressure with the same amount of particles as you heat this piston, so let me apply some heat here, and what we'll see is that the volume of the gas will also increase. So if I showed the same piston after the heat was applied, we'd see that the gas was taking up more volume, even though there's the same number of particles here. We still have 6 green particles of pressure because here, and he found that if you heat a gas in a closed container, say like a piston, so I've got a piston here and I'll fill it with gas, it'll be green gas. And this piston will be under constant pressure because as the atmosphere is pushing down on top of the piston, then the pressure of the gas pushing up is going to equal the atmosphere. But under constant pressure with the same amount of particles as you heat this piston, so let me apply some heat here, and what we'll see is that the volume of the gas will also increase. So if I showed the same piston after the heat was applied, we'd see that the gas was taking up more volume, even though there's the same number of particles here. We still have 6 green particles of gas. So this is what the piston would look like after the heat was applied. And so as you heat a system of gas, the volume will also increase. And in fact, the volume increases directly with the temperature, or the volume increases proportionally to the increase in temperature. And I think I can show this a little bit more clearly if I use a plot of gases increasing with temperature. And so this is what a plot of volume expansion would look like for 4 different gases as we're increasing the temperature. This pink gas would be helium. And so at about 300 degrees Celsius, this helium we can see is taking up a volume of about 5 liters right here. And as we decrease this temperature, the volume is going to decrease proportionally. This straight line is showing this down to at 0 degrees Celsius. We've got just a little over 3 liters that this helium's taking up. And then we've got this green gas, and this might be methane. And we're seeing the same thing. As we increase the temperature, we're increasing proportionally the volume that the methane's taking up. And this blue line might indicate water vapor, water gas, steam, and this yellow line would indicate hydrogen gas. But all of these gases can be plotted in a straight line. So in y-intercept form, that would look like y equals mx plus b. And if we substitute the values that we're using in this graph, our y is our volume. So we would see that y is equal to v, and our x is our temperature. So if we fill that all the way in here, we'd have v is equal to mt plus b. Now, if you're wondering why the slopes are different, it's because the different gas samples in this example would have different number of moles. And you can also see that the lines are coming to a stopping point at different places. And that's because that all of these gases turn into liquid at different temperatures. They all have different boiling points. So with methane, the boiling point would be about negative 100 degrees Celsius, but we could kind of extrapolate this line down. And with water vapor, the boiling point is 100 degrees Celsius. So that's kind of why this straight line stopped. But we can extrapolate this line all the way down as well. And the same thing with hydrogen. And if we extrapolate these values out to find their y-intercepts or their b values, we would see something really interesting. And that's that all of them have a volume of 0 at the exact same temperature, which is negative 273.15 degrees Celsius, which is also 0 Kelvin. And so Charles' law is actually another proof that 0 Kelvin is absolute zero, because we can't have a negative volume for gas. All of these gases have to take up some volume. So the lowest temperature that we could theoretically achieve for any of these gases is negative 273.15 degrees Celsius, or 0 Kelvin. Now, if we take our equation, which is V equals mt, and now we don't need the b because our y-intercept is 0. And if we move some variables around, we'll see that V divided by T is equal to M. Or in other words, the quotient of our volume divided by our temperature is constant. It's the same volume as long as the sample size is the same, so the same number of moles, and the pressure doesn't change. And this is exactly the concept that we've applied to our ideal gas equation. So let's try to use this concept in a problem. If the volume of a piston filled with gas is 4.31 liters at 25 degrees Celsius, then what is the volume of the gas after it's heated to 50 degrees Celsius, assuming that the system doesn't experience a change in pressure? Well, what we're looking at is a change in volume related to a change in temperature, assuming constant pressure and assuming a closed system with constant moles. So this is a perfect opportunity to apply Charles' law. So we need to start with V1 over T1 is equal to V2 over T2. And again, we're just saying that the initial quotient of the volume and temperature is equal to the final quotient of the volume and temperature, because volume divided by temperature is constant. So our initial volume is 4.31 liters, and our initial temperature is 25 degrees Celsius. But when we're using the ideal gas law, we really need to be operating in Kelvin, because Kelvin allows us to not use negative values for temperature. So let's convert 25 degrees Celsius to Kelvin, and all we would do is take 25 and add 273, which would give us 298 Kelvin. So our initial temperature is 298 Kelvin, and we're looking for the final volume, so V2, and then our final temperature is 50 degrees Celsius, and we need to convert that to Kelvin. So 50 plus 273 is going to give us 323 Kelvin. And so that's the value that we'll input for our final temperature. I noticed that I put T1 here. That's actually T2. Our final temperature is 323 Kelvin. So to continue solving this, we need to multiply both sides by 323 Kelvin to isolate our final volume. So times 323 Kelvin, and that's going to allow us to completely cancel out the value on this side, and we'll cancel out our units of Kelvin on this side. And so what we have is 323 times 4.31 divided by 298, and we're retaining our value or our unit of liters, and that's going to give us a final volume of 4.67 liters. And so thanks to Jacques Charlet, we know that if we're looking at a closed system under constant pressure, then we can predict the change in volume related to the change in temperature or vice versa.
Mm. Sure.
Okay, so continuing the history of the ideal gas equation here, we get to the 19th century with an Italian chemist named Amedeo Avogadro. And actually his name was Lorenzo Romano Amedeo Carlo Avogadro de Quaregna e de Cerreto, but we're going to call him Amedeo. And Amedeo spent a bit of his time experimenting with tiny particles, and in honor of his experiments, the number of particles in 1 mole of something was named Avogadro's number, which is approximately 6.02 times 10 to the 23. And one thing that Avogadro postulated was that equal volumes of gas at the same temperature and pressure contain equal number of particles, whether those particles are atoms or molecules. So for instance, if you filled up 4 balloons to exactly 1 liter at 25 degrees Celsius with different gases, so let's have a green balloon, and we can say that this green balloon is argon. And we'll have a pink balloon, and I'll try to make it the exact same size as the previous one, and we'll say it's nitrogen. And then we've got a blue balloon that we'll say is hydrogen. And again, I'm off a little bit in the sizes, but we're saying that all of these have exactly 1 liter. Okay, so continuing the history of the ideal gas equation here, we get to the 19th century with an Italian chemist named Amedeo Avogadro. And actually his name was Lorenzo Romano. I'll call him Amedeo. And Amedeo spent a bit of his time experimenting with tiny particles, and in honor of his experiments, the number of particles in 1 mole of something was named Avogadro's number, which is approximately 6.02 times 10 to the 23. And one thing that Avogadro postulated was that equal volumes of gas at the same temperature and pressure contain equal number of particles, whether those particles are atoms and pressure, postulated was that equal volumes of gas at the same temperature and pressure contain equal number of particles.
Equal volumes of gas contain at the same temperature and pressure. It's an equal number of particles. Okay.
Whether those particles are atoms or molecules. So for instance, if you filled up 4 balloons, to exactly 1 liter at 25 degrees Celsius with different gases. So let's have a green balloon, and we can say that this green balloon is argon. And we'll have a pink balloon, and I'll try to make it the exact same size as the previous one, and we'll say it's nitrogen. And then we've got a blue balloon that we'll say is hydrogen. And again, I'm off a little bit in the sizes, but we're saying that all of these have exactly 1 liter volume. And then our 4th balloon will be yellow, and we'll say it's filled with methane. And so what Avogadro was saying was that at 1 liter, each one of these 4 balloons would have the same number of particles. So I'm using 5 particles, but the point is that all of these balloons would have the same number of particles. And so at 1 liter, each of these balloons would contain 0.041 moles. So 0.041 moles. And if we use Avogadro's number here, that's the same thing as saying that each of these balloons would be filled with 2.5 times 10 to the 22 particles. And so if you think about it, this is the exact same thought behind our value for the molar volume at STP. We said that for any gas, 1 mole at STP would take up a volume of about 22.4 liters. And the fact that we know that this is true for any gas, not just kind of a particular gas, is credited to the work of Amedeo Avogadro. And Avogadro used this idea and some intuition to develop his law, which is V is equal to a constant A, times the number of moles, which means that the moles of gas, the number of particles of gas in a system, varies directly with the volume, or the quotient of V in N is equal to a constant. And I'm sure that you've used this same intuition when you've blown up a balloon. As you put in more air particles, as you blow more air into the balloon, the balloon gets larger. So for example, if we put in 1 mole of air particles, the balloon would be about 22.4 liters. And as we blew more air into it, say another 1/3 of a mole, we would increase the volume to 29.88 liters. So another 1/3 of a mole of air gets us up to 29.88 liters. Our volume is getting bigger. And if we were to blow even more air into this system, we would increase the volume even more. So another 1/3 of a mole of air would bring our volume up to 37.35 liters. Our volume has expanded proportionally to the amount of air that we've increased in the system. And so Avogadro's law validates the V in part of the ideal gas equation because the volume and the moles are directly proportional to each other. So let's put this principle to work in an example. So when 0.15 mole amount of air, 29.88 liters. So another 1/3 of a mole of air gets us up to 29.88 liters. Our volume is getting big. Which means that the moles of gas, the number of particles of gas in the system, varies directly with the volume, or the quotient of V in N is equal to a constant. And I'm sure that you've used this same intuition when you've blown up a balloon. As you put in more air particles, as you blow more air into the balloon, the balloon gets larger. So for example, if we put in 1 mole of air particles, the balloon would be about 22.4 liters. And as we blew more air into it, say another 1/3 of a mole, we would increase the volume to 29.88 liters. So another 1/3 of a mole of air gets us up to 29.88 liters. Our volume is getting bigger. And if we were to blow even more air into this system, we would increase the volume even more. So another 1/3 of a mole of air would bring our volume up to 37.35 liters. Our volume has expanded proportionally to the amount of air that we've increased in the system. And so Avogadro's law validates the V in part of the ideal gas equation because the volume and the moles are directly proportional to each other. So let's put this principle to work in an example. So when 0.15 moles of helium gas are added to a piston containing
Sand table. pressure, which is 273 Kelvin, and standard temp and pressure, which is 1 atm, which is also 1 mole, is 22.4 liters. Right. If you collect 1 liter of any gas and find it contains 2.5 tenths into its 22nd molecules, then you can say that 1 liter of any gas is going to be 0.041 mole.
2 moles of another gas, by what percent does the total volume increase, assuming isothermal and isobaric conditions? So isothermal is same temperature and isobaric is same pressure. So we have same temperature, same pressure, and we're looking for the percent of volume increase related to the molar increase. And so this is a perfect opportunity to use Avogadro's law. So let's start with V1 divided by N1 is equal to V2 divided by N2. And we know this is true because Avogadro's law says that the quotient of the volume and the number of moles is constant for an ideal gas. So the initial 59.88 liters, our volume is getting bigger. And if we were to blow, even more Epler increase. And so this is a perfect constant condition, V problem, because what we see is that the increase in volume is directly proportional to the increase in moles. So for the divided by the initial volume is going to give us the percent change. And so we know that this is equal to the percent change in the number of moles. So we can say N2 minus N1 divided by N1. And this really gets us to a point where we can use the values in the formula because it gives us an initial number of particles, an initial moles, and it gives us the change in moles. And so we had the final moles as well. So to find the final moles, because it just says that 0.15 moles are added to 0.82. We'll need to add those together. So 0.82 plus 0.15 plus 0.15 is equal to 0.97. So 0.97 is our final number of moles. That would be our N2. So let's substitute these values in. Our final moles is 0.97 minus our initial moles, which is 0.82, divided by our initial moles. And that's going to give us 0.15 divided by 0.82. Now we're at a point where we can solve this and we can just kind of evaluate this expression, and that would give us the total or the percent of the total volume increase. But I want to take a second. I want to think about how we could think about this kind of with some common sense and use rounding to give us an approximate answer. So 0.15 divided by 0.82 is between 0.15 divided by 1 and 0.15 divided by 0.75. And 0.15 divided by 1 is 15%. And 0.15 divided by 0.75, it goes into 0.75 5 times. And so that would give us 20% because 1/5 is 20%. And so if we had to think about this expression in a hurry, say on a test, and we didn't have a calculator, we could use rounding to get us a pretty approximate answer. We know that the answer is between 15 and 20%. And it turns out that that actual answer, if you do use a calculator, is really close to 18.3%. So when 0.15 moles of helium gas are added to a piston containing 0.82 moles of another gas, by what percent does the total volume increase? Well, it's just about exactly 18.3%. And we were able to solve this problem with a little bit of critical thinking based on the principles of Avogadro's law.
We have so far spent many videos talking. We have a situation here where we have a 4 meter talking about the
So,
ideal.
all right, let's take like a quick 5-minute digest the information. Digest the information. We sign. After this is 3, and then yeah, we'll do smoking.
number of moles times the ideal gas constant times temperature measured in Kelvin. What we're going to do in this video is attempt to modify the ideal gas law to try to take into account when we're dealing with real gases. Gases where the volume of the actual particles are worth considering, that we don't just say they're negligible compared to the volume of the container. And intermolecular forces are something that we would like to take into consideration. So let's think about how we could modify this. And to help us a little bit, I'm just going to solve for P. So I'm going to divide both sides by volume. So we can say pressure is equal to number of moles times ideal gas constant times temperature measured in Kelvin divided by volume. So first, how would we adjust this if we want to take into account the actual volume in which the molecules can move around? Well, if we wanted to do that, we would replace this volume right over here with this volume minus the volume of the actual particles. So what's the volume of the actual particles going to be? Well, it's going to be the number of particles times some constant based on how large each of those particles are, maybe on average. And let's just call that B. So we could view this as a modified ideal gas law equation, where now all of a sudden we are taking into account the fact that these particles have some real volume to them. But of course, we also know it's not just about the volume of the particles. We also need to adjust for the intermolecular forces between the particles. And we know that in many cases, those intermolecular forces are attractive forces. And so they would take away from the pressure. And so we need some term that accounts for that, a term that accounts for taking away the pressure due to intermolecular forces. So term for intermolecular forces. Now I know what some of y'all are thinking. Do we always subtract? Might not there be some situations in which we actually have repulsive forces between particles and it would actually add to the pressure? And there could be scenarios like that. You could imagine if they all have a strong negative charge, they want to get away from each other as far as they can, and that could actually add to the pressure. In that situation, we could subtract a negative, and then that would be additive. Now, how could we take this into consideration? We know from Coulomb's law that the force between two charged particles, is going to be proportional to the charge on one particle times the charge on the other particle divided by the distance squared.
Oh, that's it, huh? Unit 15, social inequality. It ends with. Yeah. Social inequality. I think maybe this was like some time ago, way before. Because I don't know if I remember going through this. Let's assume the environment. Yeah, okay. Whatever, I need to wrong Unit 9. Yeah, Unit 9.
Now, obviously, we have so far spent many videos talking about the ideal gas law, that pressure times volume is equal to the number of moles times the ideal gas constant times temperature measured in Kelvin. What we're going to do in this video is attempt to modify the ideal gas law to try to take into account when we're dealing with real gases, gases where the volume of the actual particles are worth considering, that we don't just say they're negligible compared to the volume of the container. And intermolecular forces are something that we would like to take into consideration. We have so far spent many videos talking about the ideal gas law, that pressure times volume is equal to the number of moles times the ideal gas constant times temperature measured in Kelvin. What we're going to do in this video is attempt to modify the ideal gas law to try to take into account when we're dealing with real gases, gases where the volume of the actual particles are worth considering, that we don't just say they're negligible compared to the volume of the container. And intermolecular forces are something that we would like to take into consideration. So let's think about how we could modify this. And to help us a little bit, I'm just going to solve for P. So I'm going to divide both sides by volume. So we can say pressure is equal to the number of moles times ideal gas constant times temperature measured in Kelvin divided by volume. So first, how would we adjust this if we want to take into account the actual volume in which the molecules can move around? Well, if we wanted to do that, we would replace this volume right over here with this volume minus the volume of the actual particles. So what's the volume of the actual particles going to be? Well, it's going to be the number of particles times some constant based on how large each of those particles are on average. And let's just call that V. So we could view this as a modified ideal gas law equation, where now all of a sudden we are taking into account the fact that these particles have some real volume. But of course, we also know it's not just about the volume of the particles. We also need to adjust for the intermolecular forces between particles. And we know that in many cases, those intermolecular forces are attractive forces. And so they would take away from the pressure. And so we need some term that accounts for that, a term that accounts for taking away the pressure due to intermolecular forces. So term for intermolecular forces. Now, I know what some of y'all are thinking. Do we always subtract? Might not there be some situations in which we actually have repulsive forces between particles and would actually add to the pressure? And there could be scenarios like that. You can imagine if they all have a strong negative charge, they want to get away from each other as far as they can. That could actually add to the pressure. But in that situation, we could subtract a negative, and that would be additive. Now, how can we take this into consideration? We know from Coulomb's law that the force between two charged particles, is going to be proportional to the charge on one particle times the charge on the other particle divided by the distance squared. Now, obviously, if we're dealing with a lot of particles in a container, we're not going to be able to think about the forces between any two particles. But one way to think about it is in terms of how concentrated are the particles generally. So we're trying to think of a term that takes into account the intermolecular forces, or how we're reducing pressure because of those intermolecular forces. Maybe that can be proportional to not just the concentration of the particles, and that would be the number of particles divided by the volume, but that times itself, because we're talking about the interaction between two particles at a time, very similar to what we see in Coulomb's law, because at the end of the day, these really are just Coulomb forces. So this thing right over here is going to be proportional to concentration times itself, or we could maybe call this some constant for proportionality times n over v squared, where A would depend on the attractive forces between gas particles. And what we have just constructed, let me rewrite it again, this ideal gas equation. Actually, let me put this orange term back on the left-hand side. So if I write it this way, that pressure plus A times n over v squared is equal to nRT over the volume of our container minus the number of molecules we have times some constant B based on how large on average those molecules or those particles are. This right over here is a pretty good compensating equation for when we're dealing with more real gases, ones that have intermolecular forces, and one where the actual particles have volume. And this actually does a pretty good job. And there's a name for it. It's called the van der Waals equation. And there's many different ways you might see it. You can see it written like this, or we can try to take this blue part and get it on the left-hand side so it really looks like what we saw at the top, where there it'd be written as, I'll write it, so pressure plus some constant times the density squared, close that parentheses, times the volume minus some number of molecules times some constant is going to be equal to nRT. It's going to be equal to nRT. And all of this looks really complicated, but at the end of the day, it is just our ideal gas law modified for intermolecular forces and the actual volume of the particles. Per meter cubed container, let's say that's a balloon of some sort. Instead of having just one type of molecule of gas in the container, we have three molecules of gas. We have some oxygen molecule, some hydrogen molecule, and some nitrogen molecule. And what the problem tells us is we have 2.1 total kilograms of gas. And of that, by mass, 30.48% is oxygen, 2.86% is hydrogen molecules, and 66.67% is nitrogen. Now, we need to figure out, and it's all at standard temperature at least, 0 degrees Celsius, which we know is 273 Kelvin. But we need to figure out what is the total pressure. We have a situation here where we have a 4 meter cubed container. Let's say that's a balloon of some sort. Instead of having just one type of molecule of gas in the container, we have three molecules of gas. We have some oxygen molecule, some hydrogen molecule, and some nitrogen molecule.
And what the problem tells us is we have 2.1 total kilograms of gas. And of that, by mass, 30.48% is oxygen, 2.86% is hydrogen molecules, and 66.67% is nitrogen. Now, we need to figure out, and it's all at standard temperature at least, it's 0 degrees Celsius, which we know is 273 Kelvin. But we need to figure out what is the total pressure in the container, or being exerted on the surface of the container. And then this is the new concept. We want to figure out the partial pressures of each of these gases. Essentially, how much are each of these gases contributing to the total pressure? And you can imagine this is a container, and each of these are three types of gases. Some of the pressure is going to be from the blue, maybe oxygen is the blue gas, from the blue gas bumping into the walls. Some of the pressure is going to be from the hydrogen bumping into the wall, because that's these yellow gases. And some of the pressure is going to be from the nitrogen bumping into the walls. See, that's the brown gas. So the partial pressure is a partial, you see the partial pressure due to nitrogen, that's the pressure just due to the brown particles bumping into the walls. So let's see if we can figure this out. So the first thing to figure out the total pressure, we have to figure out the total moles of molecules we have. So how, and the easiest way I can figure out the total number of moles is figure out the moles of each of these molecules. So if we have 2.1 kilograms of gas, let me write this down. If we have 2.1, so if we're just dealing with 200 moles of nitrogen, we have let me do the nitrogen color. Moles of nitrogen. We know that 66.67% of this, we say 2.1 kilograms or 2,100 grams, we know that that's nitrogen. So let's do it in grams. Because when we talk about molecular mass, it's always in grams. It doesn't have to be, there could be some lots of different atomic mass units and mass in our world. So this is 2/3. So 2/3 of 2,100, that's 1,400 grams of N2. Now what's the molar mass of this nitrogen molecule? Well, we know that the atomic mass of nitrogen is 14. So this molecule has two nitrogens. So its atomic mass is 28. So one of these molecules will have a mass of 28 atomic mass units, or 1 mole of N2 would have a mass of 28 grams. So 1 mole is 28 grams. We have 1,400 grams. So we have, or we say grams per mole. So if we want to keep our units right. So if we say 1,400 total grams, divided by 28 grams per mole, we have 50 moles of N2. You can write that right there. 50 moles. All right, let's figure out, let's do oxygen next. So we do the same process over again. 30% is oxygen. So we take oxygen down here, O2. So we take 30%. Remember, these percentages I gave you, these are the percentages of the total mass, not the percentage of the moles. So we have to figure out what the moles are. So 30.48% of 2,100 grams is equal to 640 grams. And then what is the mass of 1 mole of oxygen gas, the oxygen gas molecule? The atomic mass of one oxygen atom is 16. You can look it up in the periodic table. You should probably be pretty familiar with it by now. So the atomic mass of this molecule is 32 atomic mass units. So 1 mole of O2 is going to be 32 grams. We have 640 grams. How many moles do we have? 640 divided by 32 is equal to, that's 20. We have 20 moles of oxygen. Let me write that down. We have 20 moles. Now we just have to figure out the hydrogen. This 2% of that 2,100 grams is 60 grams. And then what's the molar mass of one hydrogen is H2? So we know that the hydrogen atom by itself has mass of 1, doesn't have a neutron in most cases. So the atomic mass of this is 2, or the molar mass of this is 2 grams. So 1 mole of H2 is equal to 2 grams. So 1 mole is 2 grams, we have 60 grams. So we really have 60 divided by 2, we have 30 moles. 30 moles. So this is interesting. Even though hydrogen was a super small fraction of the total mass of the gas that we have inside the container, we actually have more actual particles, more actual molecules of hydrogen than we do of oxygen. That's because each molecule of hydrogen only has an atomic mass of 2 atomic mass units, while each molecule of oxygen is 32. There's 2 oxygen atoms. So already we're seeing we actually have more particles due to hydrogen than due to oxygen. The particles are what matter, not the mass when we talk about part pressure and partial pressure. So the first thing we think about is how many total moles of gas, how many total particles do we have bouncing around? 20 moles of oxygen, 30 moles of hydrogen, 50 moles of nitrogen gas. Add them up, we have 100 moles of gas. So if we want to figure out the total pressure first, we can just apply this 100 moles. Let me erase this. I want to keep the problem statement there the whole time. Erase this. There you go. There you go. And erase it so you're not seeing off the screen. And now I'm ready. So we have 100 moles. So we just do our PV is equal to nRT. We're trying to solve for P. P times 4 meters cubed is equal to N. N is the number of moles. We have 100 moles is equal to 100 moles times R. I'll put a blank there for R to figure out which R we want to use. Times temperature. Remember, we have to do it in Kelvin. So it's 0 degrees Celsius is 273 degrees Kelvin. And then which R do we use? So I always like to write my R's down here. So we're dealing with meters cubed. We're not dealing with liters. So let's use this one. 8.3145 meters cubed pascals per mole Kelvin. So this is 8.3145. And the units there, which maybe I should do this. Oh, I don't want to do that yellow. The units there, I think I should keep. These are in meters cubed pascals divided by moles Kelvin. And then our temperature was 273 Kelvin. Now let's do a little dimensional analysis to make sure that we're doing things right. These meters cancel out with those meters. We divide both sides of the equation by meters. These moles cancel with these moles. Moles in the numerator, moles in the denominator. Kelvin in the numerator, Kelvin in the denominator. And all we're left with is pascals, which is good because that is a unit of pressure. So we get 4. So if we divide both sides of the equation by 4, we get P is equal to, I'll divide 100 by 4. 25 times 8.3145 times 273. And the only unit we were left with was pascals, which is nice because that's the unit of pressure. So let's do the math. 25 times 8.3145 times 273 is equal to 56,746. 56,746 pascals. And that might seem like a crazy number, but the pascal is actually a very small amount of pressure. It actually turns out that 101,000, I think it's 325 pascals is equal to, or 101 is equal to 1 atmosphere. So if we want to figure out how many atmospheres this is, we can just divide that by 100, that large number. I think that's right. Let me look it up on this table. So 101,325. So if we want to put this in, we can write this in kilopascals. So that's 56.746 kilopascals. Or if we want it in atmospheres, we just take 56,746 divided by 101,325 equals 0.56 atmospheres. So that's the total pressure being exerted from all of the gases. I don't need that picture. So this is the total pressure. So our question is, what's the partial pressure? We can use either of these numbers. There's some different units. What's the partial pressure of, say, nitrogen? Well, even though 66, 2/3 of the mass is nitrogen, only 50% of the actual particles are nitrogen. So 50% of the pressure is due to the nitrogen particles. Remember, we have to convert everything to moles. We only care about the number of particles. So you want to know the partial pressure partial pressure due to the nitrogen molecules is 50% of these. So it's it's 28,300 and let's just say it's roughly 28,000 by 373 pascals. That's roughly half of this, approximately 28.4 kilopascals, or approximately 0.28 atmospheres. And then finally, if you want to figure out the partial pressure due to a different color, the pressure due to the hydrogen atoms, the partial pressure due to the hydrogen atoms. Hydrogen, even though it's a very small part of the mass, it actually represents 30% of the molecules. And it's the molecules that are bumping into things. We don't care so much about the mass. So 30% of the molecules, remember, when we talk about kinetic energy, if something with a small mass is the same kinetic energy, it's actually moving faster. So when we talk about temperature, that's average kinetic energy. So maybe in this, we can imagine that the hydrogen might be moving faster than the nitrogen or the oxygen. We don't think about that too much right now. But the partial pressure due to hydrogen is just 30% of any of these numbers. Pick one, so atmospheres times 0.56 is equal to 0.3 times 0.56 is equal to 0.168 atmospheres. And so the total pressure, the total pressure should be equal to the pressure of each of the partial pressures of each of the gases plus the partial pressure of oxygen plus the partial pressure of hydrogen. And so this one we figured out was 0.28 atmospheres. The oxygen was 0.112 atmospheres, and this was 0.168. And if you add these together, you will see indeed that they add to 0.56 atmospheres.
All right, guys, I think we're gonna stop here for today. Let's pick up tomorrow. Well, I'm gonna do the on-key, but I'll do it off camera, just in the bed and stuff. But let's do it. Let's pick up tomorrow, and we'll do. Let me see if I have it here. I think I do. One of the cards here. Yeah, here. This is what we'll do. And do I have anything here on this one? This is kind of the same review that I wanted to do, just kind of written differently. And this is something else, so it's fine. All right, guys, thank you so much for watching. Have a good night. I'll see you guys tomorrow morning. So, see you guys tomorrow morning. Peace. Peace out.